So I'd like to welcome you to the Royal Swedish Academy of Sciences and our Sweden-Ukraine conference on theoretical and computational physics. And I just want to, before I go further, I just want to thank, first of all, the Academy, because they are funding this meeting. Then I would like to thank Erik, Aurell, and Larissa, because it's really, this conference is really a result of something that started already in November 2023 when we were, Erik, I and my wife Viktoriya, we visited Kyiv and School 145. And Erik stayed for another day and he gave a talk at the Bogolyubov Institute, and that was the beginning of a series of Zoom seminars that in particular Erik and Larissa has organized. And I think it has worked very well. I can only recall one time where you had to turn your electricity system into your reserve. Otherwise it has worked fine with, and we have had speakers from Lviv, Kyiv and Kharkiv. And we have also, and of course from Sweden, different places in Sweden. And also a few times we went to other countries. For example, last time on cosmology, you had the pleasure to listen to Slava Mukhanov. Then I would like to thank Peter Brandén, sitting up there, because he has really been very helpful in organizing this trip. You know, train tickets, flight tickets, hotel rooms, taxis, and everything Peter has taken care of. So thank you very much, Peter. It will have been, yes. And then finally, Anders Erik sitting here, who has been together with me making the application to the Academy. There has to be 2 members of the Academy making an application. So Anders assisted me in this, and he will chair the afternoon session. And I can also mention that Anders is a present member of the Nobel Committee for Physics. So if you want to know more about the Nobel Prize, you consult Anders. And he will be here for the full day and for the dinner this night. So the question is, where are we now? Well, obviously you know that you are at the Academy. But this lecture hall is quite new. It had a quite different design earlier. And what important decisions are taken in this very room? Well, this is the very room where you take the decision about the Nobel Prize.
Like we know.
Yes, like now. So what happens is that there is a meeting, usually in the early October, first physics here and then chemistry. And, of course, a lot of groundwork has been done by the Nobel committees. But here, the Academy in Pleno meets, and they take the decision about the Nobel Prize. And I'm not allowed to reveal anything from recent. I mean, yes, Larissa, I cannot reveal. I will tell you a story in a little while. One can go back in time. The archive is closed for 50 years, but if you go further back, there has been occasions when the committee has proposed certain candidate, and somebody, which is perfectly possible, some member of the Academy stands up and say, I don't like that proposal, I think we should go for this instead. And it has happened that it changed, actually. It's difficult to understand exactly how the discussion is going because they don't keep a detailed protocol. Mm-hmm. The only thing which is minuted from the meeting is what is the outcome, who was selected for the prize. And this decision cannot be appealed, it's final. And directly after the decision has been taken, a small delegation goes to a room which is very close to here. I will point it out during the coffee break. And then there we gather around the table and we make a phone call to the laureates. Because the idea is that they should learn about that they have been awarded the prize before it's announced on a press conference. After we have, it's not always possible to reach the candidates. I mean, some they could be traveling and so on and so forth. But we make an attempt to reach them. And after this phone call has been made, then we go to another room that some of you will see later after we close the session, you will see this room where we have the press conference. And I will explain then to you how the press conference works. So that's where we are. And since I'm not allowed to reveal discussions, but I will tell you a story that at least all the Ukrainian delegation will understand very well. This was in 2010. Do you know who was awarded the prize? It was for graphene. One of the prize winners was André Game. The other one caused some problems because nobody understood how to pronounce his name. The reason being that, and I checked this in Wikipedia before I went here for the decision, his name was only available in Latin alphabet, not in Cyrillic, which means that it was not possible to understand how you should pronounce his name. And so that was a problem. We didn't, well, the president and so on didn't exactly know how to pronounce his name. When I came back from the meeting, already had his name now appeared in Cyrillic. So I understood that his name is Kostya Navasolov. But still, not everybody reads Cyrillic. So later in the afternoon, I heard somebody say, well, now we understand how to pronounce his name. It should be pronounced Novosyolov. So it's not easy with Cyrillic and pronunciation. So that was a small story, just a curiosity, of course, from when Kostya got the Nobel Prize. I think that I should not continue to speak more. I think we have given the credit. And we have a program that... can we get the program up? So I just make some comments about the program. This is my last slide. I don't have any more. Yes, here we have the program. So the first speaker will be Erik Aurell, and the last speaker will also concern, shall we say, more history. Erik will talk about the thermodynamics that was born last year and now 200 years old. And Larissa at the end will talk about 190 years of waves of translation in 50 years of the David of solitons. So that will also be a little bit historical touch. We will have two talks before the coffee break. The coffee break will be just outside here. And you can stand with a small table and drink coffee and talk. And then we have one talk after coffee break. And then finally we have a lunch. This will be a buffet lunch in something that we call Club Villan. It's very close to here. You don't need to put on any coats or anything. It's just down the stairs and then to the left where you came. So it's very short. It will be a type of buffet type of lunch.
No, Mats, the lunch
Yes.
will be here, outside.
Aha, the lunch will be here.
Yes.
Okay, sorry.
Yes.
Then I... good.
Yes,
Good that you
yes,
correct me.
yes.
Good.
So no need to walk.
Okay, then it's even easier. You will have lunch outside here. And then we have just 3 talks in the afternoon. 2 talks, coffee break, and then the final talk, and then we close the session. And then some of you will stay for the conference dinner. And that will be in Club Villan, Peter, right?
Yes, yes.
Yeah, that will be in Club Villan. But I also understand that part of the delegation will go to the Royal Institute of Technology together with Erik to sign some memorandum of understanding. So that's also very good. So I think I now leave the floor to Erik Aurell, and we will learn more about the history of thermodynamics. Thank you.
Thank you. Okay. So now, how does this work?
One moment, Erik. We will start from up here.
Okay. Now let's see if I understand how this fantastic thing works. So thank you very much, Mats, for the introduction, and thanks to the Academy for making this possible. It's very nice that we could also meet in person and not only over Zoom. And a special thanks to Larissa, who is both here in person and on photo. Yeah, let's see now. No, it doesn't seem to work. somehow. The red pointer is gone. Maybe it's, yeah, I think I'm pointing. So
No,
here, yeah, if you don't know. I would say that even more than the visit to Bogolyubov Institute, I think this whole activity is an outcome of a subway ride from the Bogolyubov Institute to Kyiv, which we did together. So we discussed on the subway, and from this, of course, when we decided that it would be nice to keep the contact and to arrange meetings, which we first have done on Zoom, also at one time through the European Physical Society, and then through the Swedish community. And of course, many thanks to Mats and Viktoriya, who asked me to come along to this visit to School 145, which of course I said yes, but I didn't know what I would expect. So then this is the beginning of. And the reason I'm talking about thermodynamics 200 years, I'm not working very much into history of science, but as you probably know, thermodynamics usually counts as starting with the treatise of the book by Carnot, which was published 201 years ago. And I was invited to the 200-year celebration at the École Polytechnique last year, and then I, of course, had to prepare something on the history. And I've skipped a little bit of the history, namely the one pertaining to the Karateodori theory, which I will not speak about today. So I will speak about other aspects of the history. So here's a little bit of the Einstein quote. I think we all know this quote, but it's well worth reading in entirety. So that's Einstein's appreciation of thermodynamics, classical thermodynamics. This is the quote in its entirety, translated into English. And of course, it's of course cited very often in different contexts, but in particular, I've highlighted here at the end that it is, he says, the only physical theory of universal content concerning which I'm convinced that within the framework of the applicability of its basic concepts, it will never be overthrown. It's a pretty strong statement. And the classical thermodynamics is usually associated with many names, but in particular with Carnot himself. You can see with a very flattering portrait of him as a young man, as a cadet somewhere, and Clausius, Maxwell, Boltzmann, and Gibbs. And today I will mainly speak of the ones in the red, which is Carnot and Clausius, and as being more in thermodynamics and not so much about the statistical mechanics. Now let's see if it works here. Okay. So here's some beautiful pictures prepared for the conference that was held in September last year. There's a banner for the conference with the same version of the same portrait. There is a picture of the book, of the frontispiece of the book. There is his own handwriting of the title. Originally, he wrote, it says, in French, réflexion sur la puissance motrice du feu et sur les machines propres à développer cette puissance, which means reflections on the motive power of fire. Feu means fire. But originally, he did actually write chaleur, which is heat, and then he crossed it out. And that you can see if now this thing here works. Now this time, if you can see here, he has crossed out chaleur and has written feu instead. You can find this book, but you can also find the most easy way to find it online. It's when it was republished in a journal, more or less half a century after it was published in 1872. So a little bit about Sadi Carnot himself. He is one of those scientists in the early era who had, in many ways, a rather tragic life. He died quite young. Perhaps of cholera. It's not quite sure actually what he died of. His career, which I will mention a little bit on the other side, was in fact consists of only one book, which is the book he's famous for. And what's in this book? It's a text written in very beautiful French. If you know French, it's a pleasure to read, especially the introduction. And it starts from steam engines. And I will have a translation, a slightly changed translation into both English and Ukrainian of these two parts, which you can find. First, the opening phrase says that nobody can ignore that heat can be the cause of movement, and that it even has a great power, motive power, and that the steam engines, which are today so widely used, is a proof which we have in front of our eyes all the time. So I will have a translation into this, slightly changed towards the end of the talk, into English and Ukrainian. And also the next one says that the study of these machines is of the highest interest. His education was that of a military engineer at the École Polytechnique. So he had a great interest in machines. And that is somehow, and that was also quite clearly in the memorial conference, a family history. His father, Lazare Carnot, was a mathematician and an author of several books before the revolution. Then at the revolution, he was a member of the Robespierre party and voted the death of the king. Then he fell out with Robespierre, was almost killed by himself, and was for a while director, which means kind of a president of France between the revolution, between Robespierre and Napoleon. And at that time, he, of course, as all revolutionaries, he occupied an important palace, namely the small Luxembourg Palace in Paris, the Petit Luxembourg. And that's, in fact, where Sadi Carnot was born. So now Lazare Carnot didn't really get along so well with Napoleon. And for a while, he was kind of on kind of semi-retirement, where he spent a lot of time on developing teaching and education in the New France, and also the education of his two sons. So he started École Polytechnique. He's one of the founders of École Polytechnique, which is one reason, of course, why École Polytechnique almost puts Lazare Carnot on the same level as Sadi Carnot. And Sadi Carnot entered in the school when he was 16, which was the earliest time that he could do it. Then towards the end of his life, he did come back to Napoleon, and he was the last minister of war of Napoleon when Napoleon came back from Elba. Then, of course, he had to go into exile, and he died in he died, I believe, the year before the Carnot's book was published. So, as Sadi Carnot had a military engineering education, he, of course, was taken into the new Royal Army, but they didn't give him much to do because, of course, they didn't trust him very much. So, for several years, he was on leave, but he still received 2/3 of his pay. And it was during this time that he started to take the interest in steam engines. And in particular, why are the steam engines of Britain so much better than the French steam engines? So that's what the whole book starts with, a homage to England and to the great English engineers who have made steam engines so fantastic. And of course, if understood, if our steam engines would have been as good as the British, maybe the big wars in which my father fought for so many times. He also fought in one of the last, Sadi Carnot also fought in one of the last battles of the Napoleonic era. So he died quite young. He printed his book in 600 copies. Not so many of us sold. He had to pay the whole edition himself. And since he died of cholera, all his remaining papers were burned after his death, almost all of them. So it's not really known what else he did. His son was a successful politician, and his nephew was actually an even more successful politician. He became even president of the Third Republic in France. So if you see a street or place name in France named after Carnot, it's actually nowhere Sadi Carnot, the physicist. Is Lazare Carnot, the general and the revolutionary hero, or Sadi Carnot, the president, nephew of Sadi? If you wonder why the name Sadi, well, he's named after the Persian poet Saadi, who was very popular in this time in the Enlightenment. So that's a family history of war and peace. And why are the English so good? I think this is at least a big motivation for the whole thing. And so what's in the book? It has, I would say, except for the language, it has a lot of mathematics, but it's really difficult to follow. It's very old. Very many detailed expressions of quotients of numbers, which don't mean so much to us today. But it has one big statement, which is that the production of heat alone is not sufficient to give birth to impelling power. It's necessary that should also be cold. Without it, the heat would be useless. That means it's heat flow from hot to cold that allows heat to do work and makes it useful. And also that the maximum that you can achieve by any machine doesn't matter which kind of medium that you have. He calls that proposition générale, general statement. He doesn't call it an axiom, but this is the way he writes it. And to demonstrate it, he introduced the famous Carnot cycle in a design, which you find there copied in. The PV diagram of the Carnot cycle is actually not in Carnot. So that was a later invention of Clapeyron. And I think these are the two things that one can, as a modern physicist, take from this book. Three things: the language, the realization that you need both hot and cold, and then the Carnot cycle and the consequences of the Carnot cycle. So a quarter of a century later, we find the next person I'd like to talk about here in this review of early thermodynamics. It's the German physicist Clausius, who I realized when preparing this talk was actually a foreign member of this academy, number 445, precisely, elected in 1878, the same year as Pasteur was elected foreign member. And so he had many other honors, as you can imagine. Among the more exotic honors that he received in his life was the Iron Cross of the Emperor of Germany for services rendered in 1870 and 1871. When he was almost 50. So he wrote 9 memoirs. He calls them memoirs on thermodynamics, and he collected them in a book, which you can find on the Internet Archive. It's a very interesting book to read, and it's an enormous advancement in the presentation of the science compared to Carnot. It's like, of course, a bit old-fashioned, but it's still reading a modern colleague. Of course, every physicist knows that he invented the word entropy, but what led him to do it, and what else can one learn from these memoirs now? Way more than 150 years old. And I'm not the only one who has been struck quite recently by the clarity of these memoirs. I heard a talk by the rather well-known physicist Giovanni Lassigno in Rome in October last year, only a month after this conference, who stressed precisely the same of these 9 memoirs, not all of them, which are interesting for the argument that we have today. So among many things, let's say he also starts the book by separating thermodynamics from what we now call statistical mechanics. And it's not that he doesn't believe in that heat is actually the motion of atoms. He does. And he has other papers about that. But he says that one can discuss thermodynamics, as he will now do, without entering into the discussion of what heat actually is. So that's not in these memoirs. He has his view, which is more or less the modern view, of course, without the technical details, but that's presented in other texts. And that is, of course, the quote which I put up here. So other memoirs, again, have references to the conceptions I formed of the molecular motions, which we call heat. But in these ones here, he will, these 9 memoirs connected into published in this book, slightly afterwards, he has mentioned it's in passing, but it's not important for the argument. So the first memoir, where you find the references in the bottom, it starts with the maximum which he attributes to Carnot, which he says, in all cases where work is produced by heat, a quantity of heat proportionally to the work done is consumed, and therefore, by the expenditure of the like quantity of the work, the same amount of heat can be produced. So, saying that heat is a form of energy. And that leads to a definition that the heat expended over the work produced is some quantity A. And how did he measure, and does he discuss the measurement of work? Well, that's by the amount of work that you do by lifting 1 kilogram, that's apparently was well established, 1 meter at the Earth's surface. So it includes the gravitational acceleration at the Earth's surface, which is almost 10 meters per second square. Okay, and how does he discuss the heat? Well, that's the amount of energy needed to heat 1 kilogram of water. No, 1 gram or 1 kilogram? I think it's 1 kilogram. 1 kilogram of water, 1 degree, starting from 0 degree to 1 degree. Okay, so as we now know, the calorie. So that's the first thing when you read this book, you see that he then has a discussion and he ends up by, okay, this coefficient is 431, and for the kilocalories, we remember something like 4,000, you know? And so the reason, what's the difference? The difference is the acceleration of gravitational acceleration at the Earth's surface. So there is a calculation. I've written that the calculation is not so easy to follow. Actually, there are 2 calculations. So there's one calculation which relates this quantity A to the difference in the specific heats of an ideal gas. That's easy to follow, but it's not very precise because the numbers were not very accurate at that time. And it says that it could be anything between 350 and 480 or something like that. And then he has another one, which is that calculation is hard to follow, about water vapor, and that ends with a number which he claims is 1 over A here is 431. And then he compares to experiments by Joule, and in different ways Joule had measured this friction and found more or less the same. I think this is why he became famous for this memoir. He was able to, from theory, compute the numbers which were known from experiments. Then he also states the first law. He introduces the PV diagrams, and he discusses them, and he computes the amount of heat that's done, how much work is done. This is not completely new at the time. Clapeyron had done it before. But the first law, this is the first time that the first law is stated. It's stated in the appendix, published separately to the first memoir. So that's the first memoir of Clausius. The fourth memoir is maybe not the most famous one, but I would say, and I think also Jonas Larsson agreed on this, it's the most important one. It's the one where he states the second law as a principle, in the sense that heat can never by itself move from a colder body to a warmer body. And he introduces a quantity which he here calls equivalenzwert, or equivalence value. And he says 2 reversible processes are called equivalent if they can be replaced one by the other. And they are characterized by an equivalence value, so a number. And this number is then found to be what we today call entropy. But that's not the number. That's not the word used in the fourth memoir. So you can find, because the equivalence value is the heat divided by the temperature, and if there are several sequences at different temperatures, you have an integral, which is then called n, integral over some cycle with some heat that's moving from the system or into the system divided by the temperature. And he also says that for a reversible cyclic process, the equation is stated that the integral along the cycle of the changes of the entropy is 0. So he doesn't really say what this T, the denominator, is. He says it should be a function of the temperature alone, and by temperature he means temperature measured in centigrade, in degrees Kelvin, Celsius. And then eventually, by an example from an ideal gas, he says that probably this T is in fact absolute temperature, which he writes as 273 plus the temperature in centigrade. So this is the really important paper, I would say. But then there are there's another paper which is more famous because he invents a new name. But before we get there, I will just make 2 statements, repeat 2 statements from the 5th and the 6th memoir. In the 5th memoir, which is about something else, so it's not really relevant to this strain of talk. He states the Carnot efficiency, and he derives Carnot efficiency. This was not completely new at the time. It's been done according to Clausius by not only Clapeyron, but also Thomson and Rankin. If it was done by Carnot himself is unclear. It's not written in the treatise, in the reflections on heat. It may well have been in some of the papers which was unpublished when he died, and since those published were burned, we will never know. But it's unclear if he actually knew this formula. But it's a formula which says that the maximum efficiency of a process, and of course the Q over A, the A there is the proportionality coefficient between how he measured work and how he measured heat. W is work, Q is heat, and then you have this difference in temperature divided by the highest temperature. So it's a function only of the two temperatures, which was the proposition of that it was some function was stated by Carnot, but not that it necessarily was this simple function. And then also in the sixth memoir, he extends the reasoning from the fourth memoir, but by reading the text, you realize that he felt that he had simplified things to make it understandable in the fourth memoir. So he doesn't really say that this is new, but he does state that for a general cyclic process, this cyclic integral, the changes of the entropy are not necessarily zero, but they are never negative. And so there is the integral of dqt, which is, of course, a statement of the second law. And then comes the ninth memoir, which introduces now a new symbol for the same quantity, namely entropy, S, new name, entropy, and a new symbol, S. And ends, which I believe might, still after 160 years, might well be one of the most far-reaching conclusions ever to be stated in any paper. It beats hardly anything, so it's worth reading if you haven't read it. For the present, I will confine myself to the statement of one result. This is, you want to extrapolate from thinking about steam engines and Carnot cycles to the whole universe. If for the entire universe we conceive the same magnitude to be determined consistently and with due regard to all circumstances for which for a single body I've called entropy, and if at the same time we introduce the other and simpler conception of energy, it was pretty new at the time, we may express in the following manner the fundamental laws of the universe, which correspond to the two fundamental theorems on the mechanical theory of heat. Energy of the universe is constant. Entropy of the universe tends to a maximum. And that's, I think, may well be the statements to which Einstein implicitly referred to, that they are a theory of fundamental importance and which will never be overthrown. Likely. So after this excursion into things more than 150 years old, 200 years old, up to 160 years old, why think about thermodynamics today? And I will give some stories. Why consider, for instance, thermodynamics separately from statistical mechanics, as Clausius did very cleanly in the preface to his book? Why would we do that? When we teach thermodynamics, very often we teach it as a consequence of statistical mechanics. We start often as physicists thinking statistical mechanics first, and then thermodynamics comes as an afterthought, or maybe as something a bit more old-fashioned. At least that's the way I was taught, or that's the way I learned the subject. And I think many of the Swedish in the audience probably have the same or a very similar experience. So there's one reason. I will give some examples. So in engineering, it's still often more convenient to think about thermodynamics. Engineers who work in heat exchange, maybe they don't know so much about statistical mechanics as we do, but they may well know much more about thermodynamics, especially in practice. So for optimizing an engine, you typically do not need to know the fundamental physics. And I will give an example, which is a very interesting example, I think, where in the sociology of science, because that's a statement which started in engineering and has had a kind of nice career in the last 20 years or so in statistical physics, in physics, in fact. Then there is the very important development in sometimes known as fluctuation relations, entropy production in environment, and equalities in out of equilibrium thermodynamics. This is an important part of modern statistical physics, which at the invitation of Anders, I was happy to give a presentation about this in this same room some time ago. Or maybe it was a different room, I forget. Maybe it was the other room. Anyway, some time ago. This is an important advance, and where the, of course, both these things are related to out of equilibrium processes. And we are not thinking about equilibrium distributions necessarily. So maybe also there are maybe you don't always know the statistical mechanics of everything in physics. And in fact, there is one famous such thing, which I will get to. And maybe we have new industries which evade their Carnot, which steam engines is probably not the right thing for today, but maybe we have other things. And then if I still have some time, I will also give some touch upon a little bit things I've done myself and a bit of other colleagues here in Stockholm. Where, but if I run out of time, I can stop after other possible industries. So let's say the first example is efficiency at maximum power. And as you know, Carnot efficiency is achieved for a reversible process. And when a process is reversible, that's when they go slow enough. And so the power of this device, which is the work that's done by the time it takes to complete the cycle, is in fact zero. So it's completely useless as an engine, for instance, as a steam engine, because it has zero power. On the other hand, if you take a very, very fast cycle, if you think about it, if you have a very fast cycle, it's practically as if the hot bath and the cold bath are in contact directly. They are just using this very fast cycle to connect heat. So it will also deliver no useful work. And so again, the efficiency, the zero power is also zero. So it's clear that a practical machine should somehow work at an intermediate time scale. That's, and then, of course, it will not be in the Carnot machine. I mean, it does not be an optimal Carnot machine. And even more, there's another, if you remember the Carnot cycle, you have a hot bath, and then you say, okay, I put the system that you're considering in touch with the hot bath, and they have the same temperature. But if they have the same temperature, why would any heat flow from one to the other? It won't. It will actually not absorb any heat. So there has to be some temperature difference between the system under consideration and the reservoir for heat, for their heat to flow from the hot one into the system and from the system into the cold one. There has to be, sometimes this is formulated by one temperature, sometimes it's formulated by two temperatures. Here there's a design, very nice one, which I found on there was a conference in Paris 10 years ago, more or less, with some reviews of what happened on this. And it has a nice statement of this idea, this picture that you see. So if you then if you model the heat flow as by Fourier law, so that the heat that flows from one body to the other body is proportional to the temperature difference with the proportionality, which is the heat conduction coefficient between those two bodies, then you have an optimization problem that you can find given these material parameters, which are the conductivities from the hot bath to the system and from the system to the cold bath, and then you can optimize of the temperatures of the bath when it's close to the hot bath, when it's close to the slow bath, and so on. And if you optimize this in linear thermodynamics, you arrive at a different formula. So it's no longer Carnot. The formula of the efficiency of an engine at maximum power, sorry, this is the one we should use, yeah, is actually this formula here. So it's not 1 minus the ratio of the temperature, it's 1 minus the square root of the ratio of the temperature. And this was, in fact, probably, but there are claims of even earlier priorities of this, but it was probably invented first by the French physicist Yvon to describe the new atomic station in Saclay. It's the same Yvon who worked on statistical mechanics. There's the famous expansion, which has the name of Yvon and Bogolyubov usually. And then, more or less at the same time, it was discovered in the Soviet Union by a person called Novikov, published in Atomная Energia. I don't know if he was Russian or Ukrainian, or I don't know. I haven't been able to find. But in the West, this is very often attributed to Curzon and Alborn, two American physicists who published on this in American Journal of Physics in 1975. And then it was republished and made much more popular by Chris van den Broek, the late Chris van den Broek, in 2005. And there's been a large literature on many different models, and it turns out that it's not only linear thermodynamics. It's not clear that it's probably not as universal as the Carnot formula, but it's a pretty universal formula also. And this is a formula which, in thermodynamics, which has little to do with statistical mechanics. At least equilibrium statistical mechanics. Okay, so that's one example. Also, of course, all these people who worked on this before were engineers. Up to van den Broek, who was a physicist. And the second example, of course, or I will talk a little bit about time reversal and entropy production as one of the ways to understand the whole field of fluctuation relations and stochastic thermodynamics. So just to rehearse a little bit, if you have a Hamiltonian system given by equations, q dot is the partial derivative with respect to p of the Hamiltonian, and p dot is the minus the partial derivative with respect to q of the Hamiltonian. So this is q dot is p over m for standard forces and this standard Hamiltonians, and this is the force. Well, the time reversal of Newton's equation of motion, or Hamilton's equation as written here, is that you take t goes to minus t, q goes to q, p goes to p, minus p, and then the Hamiltonian goes to itself, the force goes to itself, and then the forms of the equation of motion are reproduced. So this is the way that the equations of mechanics are time reversal invariant. Now, if you have contact with the environment, if you have a bath, then the simplest model, the model that we start from when we consider these things in practice in physics is one form of the Langevin equation. So here's the Kramers-Langevin equation, or if the underdamped Langevin equation. So q dot is still equals to p over m, but p dot is a force, a friction, a conservative force, a friction, and a noise force. Okay? And of course, this noise force is delta correlated in time, and as you can see here. Okay? So here, as you probably know, one should take the time reversal of conservative and dissipative forces differently. That's the way it's usually described in non-equilibrium thermodynamics. In the more mathematical terminology, one can say here we have a stochastic differential equation, and we can change actually we can reverse its time in different ways, but the canonical one is also the one which we learn in class. And that goes then, t goes to minus t, q goes to q, p goes to minus p, force goes to force, but the friction force stays the same. So that means actually the material parameter gamma in some sense switches sign, right? Otherwise. So if you insert this, then you will find that the equation are reproduced. So with this time reversal of stochastics, if you do it this way. Okay, and it gives friction, of course. There are other ways you can do it. Some of them gives anti-friction. That's not very physical, but from a mathematical point of view, you can also reverse the time in the stochastic differential equation in a different way. So this leads to path probability ratios. You take the path, the probability of finding a path going in a forward process, and the same path in P and Q going in a backward process. And the ratio of these two paths, the probabilities of these two probabilities of the same path, is in fact related to what is in fact an entropy change. So this dq here is the energy transferred from the system to the bath by the dissipative forces, the friction and the noise, and T is the constant bath temperature. And this means that if you have weighted forward averages of what you have, the minus here, you put this over here, so the forward probability with this weighted, that's in fact the unweighted probability of the reverse process. And so those are really very simple. And you can get these famous equalities like the average of the exponential of minus work in units of kBt is exponential of minus the free energy difference between two equilibrium states in terms of kBt. That's Jarzynski equality. And for this discussion, maybe more interesting is the weighted exponential of the same dq dt, same that you have here, and then a change, which I will skip. You can read the paper, it's exactly what it is. It's a Seifert's integrated fluctuation theorem, and there's a definition of how you define the entropy, internal entropy change of the system. Anyway, so this is an equality in this model, and if you use Jensen's inequality for this exponential, you can actually get a second law which holds an expectation. So this delta cis here is the standard Shannon entropy of a probability distribution describing the system. The small delta, I've skipped for the moment what it is. And this is the expectation value. And this kind of science was invented, the very first formula of this type for a cyclic process where there's one on this side was written down by Bochkov and Kozlovlev. And I believe that Bochkov was in Nizhny Novgorod and Kozlovlev was in Donetsk. I'm not sure where he is now. As far as I know, he's still alive. But anyway, this was published in, it's not very readable paper, but it has the equation for a cyclic paper. There is a fantastically readable and very famous paper by Jarzynski, who didn't know then of Bochkov and Kozlovlev's result later, which was published in PhysRev Letters in 1997. And for the context of stochastics, there is a paper by Kurchan, which is very influential. And I have been particularly interested in this paper, a mathematical paper by Chetrit and Gavensky, the late Gavensky, who died 2 years ago. And then there's a review, which I've given you here, which also by Seifert, which discusses this in a much more physical language. So this has been a huge industry and an enormous literature. And it's also now a kind of entropy in the Clausius sense without the underlying statistical mechanics playing much of a role. And the third example I'd like to give is black holes and Hawking radiation, which my small contribution to this subject, I was happy enough to give that talk for the first time when I was visiting Kyiv. It's been published since, but I guess all physicists know that black holes exist in nature. They have been photographed in different ways. They've been known for a long time that they must exist. I think we all know also that the life of a black hole starts with a gravitational collapse. Then there's a long, slow process when it radiates, first very slowly and at the end very quickly by the Hawking process. So here there is a radiation of this temperature, there's a temperature of this radiation, which is, you have to remember 1/8 pi, and the rest is just dimensional quantities. So it's the energy in Planck mass times c squared, which is an energy, over kb is a temperature, and then it's a mass of the black hole over the Planck mass, and then it goes to -1. So that's the outcome of the calculation of Hawking, and that implies, of course, an entropy by the formula, which is not the formula of I have given so far, but it still is a thermodynamic formula. So that gives this very strange entropy, which is super extensive. If you do it for a Schwarzschild black hole, it's quadratic in the mass. And there's many attempts to construct the statistical mechanics of black hole, but the above is thermodynamics. So maybe I skipped the last count. If you count the entropy of the radiation, it's a little bit different. So anyway, it's actually not known what is the underlying statistical mechanics of this entropy. It should be, according to Boltzmann's formula, there should be a phase-space volume such that the entropy is the logarithm of the available phase-space volume. But what is that phase-space volume? It is much, much larger than the phase-space volume of the star that collapsed to a black hole. The increase in the entropy in a black hole collapse is fantastic. It's 10 to the power 19 large for the solar mass black hole. And so this, I guess, is a major mystery in fundamental physics as today. It's in some sense, it's believed there are calculations and counts of how much entropy there is in the world. And almost all the entropy in the world today is in the form of Bekenstein-Hawking entropy of very large black holes. It's like less than one part in a million is the entropy of things we know. So in that sense, most of the phase-space volume of the universe is unknown. And this, I think, beats also dark energy, which is, I don't know, what is it now? 60% of the world mass. And okay, and then dark matter is another 25% or whatever. Here we have 99.999999% of the entropy of the universe is something which nobody knows what it is. That means nobody knows in the sense of statistical mechanics what it is. So let me end by the steam engines of today. Do we have some industries that play an equally important role today as the steam engines did 200 years ago? I think we can say that we do. It's the all the industries around artificial intelligence and data generation. Not only IT in general, but this particular type of using enormous structures. And here's an old, I did actually prepare this slide a long time ago. So this is not very, this is done already in December 2019. People I used to know in Helsinki had constructed this website. This person does not exist, so it would generate any number of people's faces that look as a face, as a photo, completely okay. And it can also produce dogs and horses, I think. So of course, this you can show here on a slide, but now, today, we can generate text, which are quite good with ChatGPT. We can generate videos, and I was sharing just with Larissa just yesterday, I guess, a video uploaded some days ago on YouTube from a company, or I don't really know what they are. They're called Maryna AI. So it's a Ukrainian name. I suspect, though, that actually they're Americans and they just like the name. But I'm not sure. Maybe they are Ukrainian. Yeah, anyway. So they can make completely lifelike videos, not only pictures, but also moving pictures. So I think we have a whole big branch of industry which is not so important in Ukraine, but has been quite important in Sweden, namely the music videos, which we grew up in. And I think this whole branch of people, which employs quite a lot of people in Stockholm, actually, even, people who come out from my own university in game theory. And they are completely out of work now because you can do it much better with artificial intelligence. Here also we have some, so Carnot was worried that the Anglo-Saxon or the British dominance was very strong. And here you can see that all of these are American companies. This Silo AI was a Finnish company, but it's now been bought by AMD. So it's now AMD Silo AI. It's used to be the strongest one in the multi-language version of ChatGPT. This is Mistral, the French one, which is you can read if you read French literature, French newspapers. They are not that famous otherwise. So there's also this political angle, which is very similar to Carnot's day. So do we know why they work, even though we have two gentlemen here in the audience who gave them important prizes last fall? I would say that we know that they work. This has been demonstrated empirically. And as, of course, the English knew how to build good steam engines 200 years ago, but we do not know how they work really, and we do not really know why they work. Say, for instance, why does deep learning work for so many commercial and scientific tasks? And by preparing this, I was checking, how much if I change two words in the two sentences quoted on the first page by Carnot. So I changed machine à vapeur to intelligence artificielle, artificial intelligence, and I've changed one more word in the same sentence, and I also call them I call it les machines d'apprentissage. And then the rest is the same. And then you can, it reads very well in French, actually. It could be could work fine. And then you can translate it in Google Translate, which is, of course, also one of these artificial intelligence services, which I'm sure most of us use quite a lot. And the English, I just needed to change a little bit for the style. The content was fine, but the style needed to be changed a little bit. And so I also did the change to Ukrainian. I can understand what it says. I can say, it looks okay to me, but I am not a good judge of the style in Ukrainian. Maybe the style is off. I mean, that you are the better judge. But the contents, I think, is fine. So I think I have almost done. I will actually skip the last part because we have only 5 minutes left. And just to say that we had a very important advance in this area of thermodynamics, which is getting more appreciated now than it was in the past. And our eminent colleague Göran Lindblad is famous for the Lindblad equation and for the quantum data processing inequality. But he also wrote this I believe, very important book on non-equilibrium entropy and irreversibility. And I was fortunate enough to be able to participate in the editing of the memorial volume of this book for him, together with Ingemar Bengtsson, who is here, and then to write the first serious review of this paper. So I will skip the rest of the slides, and I will just move to the thank you slide. And so to the Academy for making this possible, to our Ukrainian colleagues, and I hope to say friends, for making the long journey to Stockholm. Let's hope that in the future, once again, there will be peace and we can go by airplane. It will only be 2 hours or so. To Larissa for all the interactions we had, and to Mats and Anders for making this possible, and a bit also to my various interlocutors and collaborators in this area. Thank you.
Thank you, Erik, for this very interesting talk. And now it's open for questions or comments. Yes, Larissa.
Erik, thank you so much for very interesting and exciting excursion into the past. And it reminded me that solitons were discovered almost at the same period. So 200 years was a great experience of the humankind, I think. But more and more we are interested in the living systems also. So I'm interested very much in the last part of your talk, which you skipped. But briefly, you showed your paper, non-equilibrium entropy. And there is term negentropy by Ilya Prigozhin. Do you distinguish these two? And the role of entropy in the living systems? Yes, I know. In generally speaking,
it's a difficult problem.
Non-equilibrium, but just your opinion, briefly.
I can. This, of course, there have been very many papers and let's say also different opinions on this and related topics. My view is kind of here, I would say is a bit pragmatic, saying that, of course, life demands non-equilibrium. So there always has to be, life is made to some extent out of Carnot engines, which flow from, there is some sort, there is some low entropy to some high entropy source. And of course, this is the sunlight is the ultimate guiding point. But of course, in this part, there are subsystems which are approximately in equilibrium. So inside the living cell, there are both equilibrium and non-equilibrium processes going on at the same time. And it depends on which process one is interested in and which time scale one is looking at, if it's more profitable to look at it as equilibrium or non-equilibrium. And if it's equilibrium, yes, there is entropy. If it's non-equilibrium, it's more unclear if the entropy concept is equally valid. And that's why, I mean, I didn't actually cover Lindblad's attempt to construct a non-equilibrium entropy, although I think it's very interesting, but he's certainly not the only one. And I would say this is a route less well traveled, yeah. And I think it's the moral still, I think, is that you can do things in thermodynamics without going to the statistical mechanics of entropy. And I think it's also interesting. Yeah.
When you say we have different processes, can we say we have different entropies?
Well, according to Lindblad, there are many different entropies describing the same process. I would be happy to explain that to you, what his idea was. Yeah, and they are related to the power of the observer, how much different controls can be related to different entropies. That's his point of view, which I think is worth being explained, which is worth to be explored more, I believe. Yeah.
So that's kind of also quantum mechanics. When
yeah. Of course, the language in Lindblad is all throughout quantum mechanics, but you can sort of, let's say, implicitly always take the classical limit and consider it also classically if you like.
Thank you.
I'll be happy to show those slides to you afterwards or in the break.
More questions? Yes,
yeah.
Please.
So we are often speaking about the thermodynamical limit. When the number of particles at degrees of freedom are going to infinity. But sometime in our institute we discussed about the thermodynamics of a finite number of degrees of freedom. What is your opinion whether it is reasonable, yes.
Yeah, yes. The whole field of stochastic thermodynamics considers that the systems under consideration are finite dimensional, often quite low dimensional, I mean, like one particle, which can be one colloidal particle. In most of these studies, there is always implicit a bath, which is practically of infinite dimensionality. But this is the outside. This is not the system itself. So the system, you can do perfectly nice thermodynamics, I would say. This fluctuation relation is good thermodynamics, but it's not built on the thermodynamic limit for the system. There is another thermodynamic limit for the bath. If you don't have an equilibrium bath, then there are many complications, and then you have many other problems. So I would say that also that I believe is also implicitly in Clausius' separation between thermodynamics and statistical mechanics. He believes, probably, although without the mathematics, because that was later, that the basis of his thermodynamics is statistical mechanics in the thermodynamic limit. I guess that this is more or less what he believed, even though he was before Boltzmann. But he doesn't use it in his memoirs. And so there are things that you can do in thermodynamics without having that discussion.
Okay, I think we have to move on, but we have, I see.
Thank you for your lecture. I have such question. If we have a few time scales, for example, like in kinetic or non-equilibrium statistical physics, can these two time scales be counted in formalism of thermodynamics?
Of course, I mean, there is a lot. Kinetic theory is a field by itself, and usually it gets more complicated the more time scales and the more details you have. And you might be a greater expert than me, but with effort, yes. Yeah. But I don't think this is really your question.
I mean in formalism of thermodynamics. Can we take into account few time scales? Fast process and...
Yeah, well, I would say that there's a finite time thermodynamics that leads to the Coulson-Alborn formula, as it usually is called now these days, although of course it was the Novikov and Yvonne formula. That's a kind of, there is a time scale, of course. There is an optimal cycle time. And this optimal cycle time, I didn't show it in the slide, but that depends on the material parameters, which are the heat conductivities between the system and the cold and the warm system. Yeah. So yeah, there's an optimal choice of those timescales for achieving maximum power. Yeah, yeah. There are several places I can point you to very nice, I mean, very clean and nice discussions also from the physical point of view of these calculations. I didn't cite all of them in the slides.
I think we should move on, but
yes,
I just have a comment, Erik.
Yeah.
Isn't it striking that the name Carnot survived 200 years? I mean, engineers would still talk about the Carnot cycle. He's not forgotten.
No. I think it's partly, actually, I think it's partly because and that I realized last year when I was at the conference, it's also for the institutional power of École Polytechnique in France, and the importance of Carnot's father, Lazare Carnot, as the founder of École Polytechnique. And then it was a very important piece of work. Yeah.
So we thank Erik again, and Viktoriya Blavatska from Lviv, and she will talk about something. I actually had to look up this word. I didn't know this word. Particle chelation by adsorbing polymers, Monte Carlo studies. I never heard that word.
Yes, I will explain what it is. It's very interesting. So, first of all, thank you to organizers for the possibility to be here. And this presentation is mostly dedicated to very simple polymer model and corresponding it's better here. And corresponding numerical approach, which nevertheless allows us to analyze a set of interesting problems of modern polymer physics. So, and one of the problems I would like to present in more details today is related to a situation when we have composite systems involving polymer macromolecules, long and flexible polymer chains, and set of particles which can be organic or not organic. So when we encounter such situations, there are a lot of possibilities. For example, this is some colloidal some colloidal suspension, micellar solution. So we have polymer chain represented by green lines here, and we have some particles, and both of them are dissolved in some kind of solution. And what is interesting here, we can distinguish between two crucially different situations. So we have size of particles, of course. This is one parameter. This is particle diameter d. And another parameter is some effective size of polymer. For example, it is a gyration radius. I will define it in more details a bit later. So when gyration radius of polymer is approximately the same as effective size of particles, so we have one, so to say, set of situations when these polymers can act, so to say, as spacers. They can separate particles in colloidal solution. They can be served as a separator between different phases. Or when these polymer chains are attractive for particles, when they are adsorbing, they can adsorb on the surface of these particles. There are a lot of problems, a lot of physical situation. Another interesting case, which actually I would discuss in more details now, is when size of particles is very small comparing with effective size of polymers. And in this case, when these particles, when we assume that polymer chains are adsorbing, so particles are attracted and adsorbed. So there is such a situation of so-called necklace. Many particles are adsorbed on long polymer chains. Why it is actually interesting for us. So actually you asked me already, what does it mean, chelation? So recently it was quite an interest towards some problem connected with cleaning of wastewater. So if we, what does it mean? So usually, what does it mean? Wastewater. Usually we have some ions of metals. For example, it was some experimental studies, mercury ions in solution, and we need to remove them somehow. So one of possibility is to use the set of adsorbing polymers, in some sense like filters. So this polymer will adsorb particles. Particles in our case are some metal ions, and then we can remove. This is one of the methods of cleaning the wastewaters. And chelation is some special mechanism of how to say, establishing bonds between monomers of polymer chain and particles, usually some covalent bond. But to go into more details, which I will not present here because my talk is concentrated on something else, so chelation is actually establishing chemical bonds between particles, some ions, which are very small comparing with polymer size, and actually the monomers of polymer chain. So now let us go more deeply a little bit how we describe this situation. And let us start with some definition. I already mentioned what is radius of effective radius of polymer. So let us go a little bit into details how we can describe the polymer macromolecule from point of view, I would say from mathematical point of view or statistical point of view. So any polymer macromolecule, it's actually a system of many small repeating units, which we call monomers, that we have n large of them, of these repeating units. So when we can consider this system from just like some mathematical system, we can prescribe a radius vector, position vector of each of these monomers. Then, of course, we can introduce center of mass of such system. This is just systems of particles, but they are connected in some special way. So here, x are coordinate in that dimensional space. We would be interested in three-dimensional space, of course, because it's mostly physical. So we can introduce center of mass of these systems of monomers, which coordinates just equal to average coordinates of all monomers. And we can introduce gyration tensor, which also has lots of interesting properties. But for the moment, what is of interest for us is gyration radius, which is actually the trace of this gyration tensor. And when we look closer in definition of this gyration radius, it gives us average deviation of positions of all monomers of polymer chain corresponding to position of center of mass. So this gyration radius, roughly speaking, is the radius of sphere which can contain our polymer macromolecules. Actually, it describe if it is larger or smaller. It means this distribution of monomers in space are more dense or more compact. So in our studies, we will use the lattice model of polymer chain. So as we see here, we consider the discrete model. So we consider polymer chain as set of repeating unit monomers. And now let us put this system, this polymer molecule on a lattice. How we can do this? We can use, so let us consider the lattice. For simplicity, just to present it, we consider two-dimensional lattice, but in fact we will consider three-dimensional cubic lattice in what follows. So let us start with some random site of the lattice and put the first monomer on it. So we have the first monomer here. And this is, then our chain will grow step by step. How it is possible? So we can see, for example, in two-dimensional lattice, there are 4 possibilities to put the next monomer. We choose one of these possibilities. And we also introduce the weight of the growing chain. The weight of chain will be equal to, we will multiply possibilities to perform each the next step, to add each the next monomer. So this our chain is growing step by step, as we see. This model is also well known in statistics as model of self-avoiding random walk. But here we will consider this as model of growing polymer chain. So as we see what is going on now, this growing trajectory is growing step by step. And what we receive at the end is something really resembling the polymer macromolecule as it was presented, for example, here. And for each configuration, because of course we can have at each how to say, so this is just one of possible configuration, of course, of this growing polymer chain. And the weight will be different for different of them. This is more compact, some of them can be more stretched, and so on. So, and actually, how we can use, what is advantage of this very simple numerical model, lattice model of polymer chain? It allows us to consider those problems where we are not so much interested in chemical structure of polymer chain and these particles, but rather this model and the method which we will use further on will allow us to study problems on a considerably large scale, where actually the microscopic details like chemical structure are not so crucial. And it will allow us to get some results which are in some sense universal for the wide range of polymer macromolecules, independent on their detailed chemical structure. So how it actually works. So this is our polymer chain, which is grown by this lattice growing algorithm, which I presented before. So how it looks like. We have n monomers connected in a chain, and how we present a solution with some particles dissolved in this solution. It's very easy to do in this lattice model. We just assume that some amount of sides of the lattice are occupied by some particles actually, and this polymer chain is avoiding them. So a polymer chain cannot cross the side if the side contains particle. So what are important parameters for us here? So P is concentration of these particles. It's actually concentration of these sides containing these blue sides, which are not allowed for polymer chain to cross. And also another, okay, of course it is length of polymer chain n large. We will also introduce in the next slide binding energy, because of course we are interested in the case when there is attraction between these particles and polymer and monomers of polymer chain. So as we noticed, this model is very, very general, and that is why it allows us to study a really wide range of problems. For example, it can be adsorption of, it can be problem connected with colloidal solution when we are interested in adsorption of colloidal particles into polymer chain. Or another problem which I mentioned and which is very interested in, which actually motivated the study, is this problem connected with cleaning the wastewater. And here we consider these particles as these waste particles of some metal ions in solution, which can be removed from solution by mechanism of chelation. So, and the next step, so how it works, as I mentioned, we are interested in the case when these particles, which are presented in solution, are adsorbed on polymer chains. How to do this within the frame of this simple lattice model. So let us introduce binding energy, epsilon small. This is binding energy between a single monomer of this our polymer chain and a single particle. So within our lattice model, we assume that particle is adsorbed on polymer chain when particle occupies a side of the lattice which is nearest neighbor to the side which is occupied by monomer of polymer chain. For example, situation like here or here. So here I present by red color those particles which are adsorbed. And each time when particle is adsorbed to polymer chain, when it is on occupying side which is nearest neighbor to the sites occupying by polymers, we prescribe some binding energy. So in such a case, we can of course introduce the total energy, adsorption energy of given polymer trajectory and particles which are adsorbed. So this is how it looks like in our computer simulation. This is actually the snapshot in 3 dimensions. So by green we present our polymer chain, which is grown by growing algorithm. Blue particles here are those ions or any small particles dissolved in solution. And by red color we present those particles which are adsorbed in present configuration. And of course, so this is, for example, we took N20 monomers. It's just very short polymer chain, just to make it more pictorial. Concentration of particles is 0.1. Usually we are interested in small concentration. And those particles which are adsorbed, of course, the number of absorbed particles will be modified depending on concentration of solution, dependent on running configuration of polymer, and of course the value of binding energy. So a little bit more details about this method. As I told, it's very simple, but it still works and works quite good. So to each configuration, let me remind how it looks like. So usually in any kind of Monte Carlo simulation, we need to perform averaging over an ensemble of different configuration. In our case, different configuration means a set of different constructed polymer chains. And also we have different configuration of lattice, because position of these particles can be also, of course, different. So we have double averaging in such kind of system. One averaging, which we called conformational averaging, is actually ensemble of different constructed polymer trajectories. And another is disorder averaging. It means different configurations of those positions of particles in our system. And also, as I mentioned, to each configuration, we prescribe attraction energy, which is dependent on the number of particles which are adsorbed to our polymer chain. So, what observables are interesting for us in this kind of problem? So the first one and mostly important one, if we are considering, actually why we are considering this kind of problems, because we are interested to clean the wastewater from as much number of waste particles as possible. So let us introduce such a quantity, which we called adsorption efficiency. Actually is the average number of particles which are adsorbed by polymer chain of a fixed length. This is actually important for us because the larger is this number, the more effective actually is our process, is our method. And to make it, so to say, more for better presentation, we introduce something which is called, so actually we normalize this value by the length of the chain and call this adsorption efficiency. Why adsorption efficiency? So the larger it is, the more effective is our polymer chains for removing particle from solution. What is interesting to discuss here? So n is length of the chain. When n is very, very small, for example, when n equal 1 is just one particle, which is adsorbing particles of these waste particles, and so on. When n is larger, of course, we restore our polymer chain. Different epsilon here is different values of binding energy. So the larger is epsilon, it means the stronger is connection between polymer and this waste particle. So the stronger they can be caught and hold. So what is interesting to notice here is that short chains are more effective in capturing particles, capturing waste particles from solution. So this efficiency is, so what does it mean? So from experimental point of view, it's more efficient to take many short polymer chains than to take very long polymer chains. One very long is less efficient than many shorts, many of them but short. Why it works like that, we can analyze in more details. So if we recall how it looks like our growing polymer chain model, and let us analyze such a quantity which is actually connected with available free space around our polymer macromolecule, because actually this available free space is connected with efficiency of this polymer chain to adsorb, to attract waste particles which are in solution. So for example, if we take polymer, so to say, polymer which contains only one monomer, of course it's very efficient because, for example, in three-dimensional lattice, it has 6 nearest neighbors which are empty. So one particle is very efficient to catch somebody, so to say, in the lattice. When we consider this, so to say, polymer chain with 2 monomers, we can see that on average the capacity of each of this monomer to capture particle is now less. It's only 5 because of covalent connection between them, right? So and so on. If we consider even longer polymer chain, we can easily see that, okay, so this I did not tell you what is the value of interest here. What is the, how to say, the effective, or rather the average number of free nearest neighbor around each monomer of polymer chain. Yes, so it's, of course, as we can see, it's the highest for single particle, and it fell down when the length of our polymer chain is growing. Because, for example, here we take 6 monomers, and we can see even how it looks like, that some monomers are already screened in some sense, and they, for these monomers, it's not so easy to capture the waste particles. So this is a special quantity which is called number of free neighbor site around polymer chain of some length, and we see it falls down with length of chain, and that is why the adsorption efficiency is falling down with increasing the chain of polymer length. So we can also consider dependence of this adsorption efficiency on binding energy. this binding energy, which actually describes how strong is connection between monomer of polymer chain and waste particle in solvent. And we can, so in this picture, we have this adsorption efficiency as function of binding energy. What is also interesting here is that, we'll see it later, when binding energy becomes strong enough, there is kind of phase transition. So the adsorption efficiency grows to some step, and then it reaches the threshold. There is actually kind of phase transition from the state when a polymer chain reaches the maximum of adsorption. It can adsorb some number of particles, which is maximum, and increasing the binding energy anymore will not produce any other results. I mentioned there is interesting property, important characteristic of polymer chains is gyration radius. When it is compact, when it is smaller, the polymer configuration is more compact, of course. When it is larger, polymer configuration is more dense and more extended in space. And it was interesting to analyze what happens with typical polymer configuration when this polymer molecule is not just in pure solution, but in solution where we have many waste particles, many these obstacles in some sense. And really we can see when binding energy, so this is radius of gyration at some fixed polymer length, I think it's like 100 monomers, as function of binding energy. So when binding energy is very small, and actually around 0, a polymer chain behave more or less like free, like in pure solvent. But when, so it's more extended in space. But as it is probably intuitively clear, of course, in situation when polymer chain is starting to adsorb this waste particle, it becomes more and more compact. So it reached this position. So in some sense, this adsorption transition, which we noticed in previous slide, it corresponds in compactification of polymer macromolecule as well. So when binding energy between particles and polymer polymer monomers is really strong, the polymer become more compact. And also we can see this by analyzing some kind of correlation between radius of polymer macromolecule and number of absorbed particle. What is actually clear here, so when polymer chain is more compact, of course it cannot adsorb so many particles because these monomers which are inside of polymer coil are screened and not available. And another, just one more quantity which is of interest in such kind of problems. So let me remind you what was our main task, to make the process of removing particles from these waste particles from solvent as efficiently as possible. So one characteristic of efficiency which was introduced before, it was actually how many particles can in fact be adsorbed by polymer chain, just the number of particles adsorbed. By another interesting characteristic, how strongly this particle is connected to polymer chain. So what does it mean? We call it chelation strands. It means, just a moment, I will come back to this lattice model. What does it mean? So we see, for example, this particle is adsorbed to polymer chain by establishing two bonds. So this waste particle is holded by polymer chain more strongly, so to say, than this one, because this one establishes only one chelation bonds, and this particle has two chelation bonds. So, and also an important characteristic in such kinds of problems, what is actually the average value of bonds established by single waste particle with polymer macromolecule. We call it average number of chelation bonds. It is also, they are also called bridge points, so just a number of direct connection, covalent bonds between particle and polymer macromolecule. And what is interesting here is that this value shows opposite behavior to number of particles which are adsorbed. Let me remind you that we found that short chains are more effective in adsorbing number of particles. So the shorter chain, the more effective number of particles it can adsorb. But when we are interested in this chelation strength, when we are interested to have more bonds between waste particle and polymer macromolecule, in this case, longer particles actually are more efficient. So experimentally, again, what is the conclusion here? If our task is to adsorb as much particle as possible from solution, it's more efficient for us to take a large number of very short chain than to comparing with taking very long polymer chain. But when we are interested in when our task is to consider situation when these waste particles are connected very strongly to polymer macromolecule, when number of these chelation bonds are large, then it's better to take very long polymer chain comparing with larger number of very short. And okay, and this what is also interesting, which is also probably intuitively we can understand why it works. So we noticed that the number of chelation bonds, of course, it's growing with number of lengths of polymer macromolecule, and it grows with this binding energy, which is also clear. So the larger is binding energy, the more connectors, these bridges, can be established between waste particle and polymer chain. But if we are interested what is probability distribution, for example, we see that mostly probable, of course, at any value of binding energy, that particle has only one bond with polymer chain. But on average, yes, and what is also important to mention, I mentioned that in this kind of problems, we noticed some kind of phase transition between adsorbed and not adsorbed states, depending on a value of binding energy or adsorption energy epsilon. So how to catch the critical value of binding energy? We can consider, of course, so as far as any kind of phase transitions or crossovers are connected with strong fluctuations, in our system, we decided to introduce the measure of fluctuation as such a dispersion of a number of adsorbed particles. And really, if we analyze such variance, depending, so here it is presented at different concentration of particles, we can find that critical value of epsilon is something around 0.5. So what does it mean? We do not need to have very strong binding energy between waste particle and polymer chain. It's enough to reach this crossover value and keep it, because even increasing it any more will not affect in any case our adsorption strengths. So let me summarize what I wanted to present you today. as you probably mentioned, it was really very simple lattice model of polymer and very simple numerical simulation method, which we did not take into account any details of chemical structure of polymer macromolecules or any details of chemical structure of these particles, which we call waste particle in solution. But still we were able to catch some, I would say, rather qualitative features which are observed in such kind of processes when we have adsorbing polymers put into solution with some concentration of waste particles which we are interested to remove from this solution by the mechanism of adsorbing these particles on polymer chain. And so some interesting conclusion which already I did during this presentation, that okay, so short polymer chains are more effective in adsorbing as much waste particle as it is possible. But on the other hand, if we are interested that this chelation, this adsorption is strong enough, we need to have also chelation strength, the number of established bonds to be quite reasonable. And for this, we need to have actually longer chain. So the mainly conclusion is in some sense that the polymer chain of some average length, not very short, but also not very long, seems to be mostly efficient to satisfy both of these conditions. And also what is interesting here is that we can observe some kind of phase transition between not adsorbed and adsorbed state. So when this parameter, which we call binding energy or adsorbing energy between waste particle and polymer macromolecule, reach some threshold value, we do not need to increase it anymore, because anyway we will not increase the adsorption strength, the adsorption efficiency of polymer macromolecules in a given problem. Okay, thank you for attention.
Thank you, Viktoriya, for this very clear and interesting presentation. Are there questions? Yes, Richard.
How difficult would it be to include the effects of branched polymers?
It's actually our present task.
Okay.
We consider now, it's nice that you asked me because it's really interesting. Now we consider so-called star polymer, when we have one center and many linear polymer branching, like centering out of it, and brush polymer, when we have long polymer chain and many other chains. It's like this tree structure. And there are also interesting regimes. We found that star polymer are more efficient in establishing these chelation bonds, but less efficient in sense of this, what I call adsorption efficiency. So they can catch less particle, first of all, because star polymer are more compact than linear polymer chain. But there are lots of interesting effects to study.
Yes.
Thank you. I have actually two maybe naive questions. First, if there is any established method to clean water from these contaminated already polymers, or is it the problem need to be done?
So far, so what we propose here is, so far is a theoretical level.
Okay.
So how it works in practice, yes, it's some kind of filters based on a set of polymer macromolecules which are adsorbing particle from solvent. But so this our task was simply to give some qualitative, mathematical, I would say, even description how this process may look like, and this what is more efficient to took short chain, large number of short chain, or less number but long chain, something like that.
Oh, okay. And the second one, maybe connected to the previous. You already told that there is difference between short and long, but you didn't explain maybe about the structure because of self-screening. Maybe there is the easier way to just use rods and package them in a very certain way to have the maximum absorption positions, and that would be the preferred solution for such a problem. Sorry.
In some sense, why polymer chain I think more efficient. Actually, we tried this also. Polymer chain, comparing with rods, they are flexible. So depending on configurations, because you know this polymer chain, when it is put in solvent, it attains different possible configuration. One possible configuration, it's really like a rod. But mostly often it's like it is called polymer coil when it is like actually it was presented here, something more compact. And actually, by averaging of different configurational space, we can easily find out that polymer chain, due to this flexibility of discovering this, because by different configuration, polymer can discover space around, which is more efficient than just taking rod, because rod is just fixed.
Yeah, but maybe there is like some very sophisticated positioning, packaging of these rods that gives eventually really more efficient absorption.
It's like rigid polymers. So we consider these rods as polymers, but so-called rigid, like hard rods.
Okay, thank you.
Yes, but actually this how to say problem was really connected with flexible polymers. It really comes out from some experimental studies, because real polymers are rather flexible, not rods. So probably it came out from this.
And how long time do you think there is going from your theoretical calculations to really practical application of this polymer cleaning technique?
Well, this technique actually is of use now, but these our results were rather aiming to give some statistical description of this process. Probably it cannot be so directly applied, but some conclusions like about this efficiency of short chain comparing with long chain, I suppose it can be of interest to some experimental or rather technology.
Okay, I don't see any more questions, so we thank Viktoriya again. We'll try to get started, although I know that there is very interesting private discussions going on, but we need to leave the floor for next speaker, which will be Maryna Pankratova. And maybe we can call you like a hybrid speaker, because you're from Ukraine, but you're active in Sweden.
Yes.
So please. And it will be about magnetism.
Yes. So I would like first to thank organizers for creating this great event and also for inviting me here. I'm very excited to present my work. And today I would like to talk about my main area of research, main area of activity, that is ultrafast magnetization dynamics. So that are our results of our group from a couple of years back. And so I would like to talk about ultrafast magnetization dynamic of ferromagnets, antiferromagnets, and ferrimagnets. I would like to start with a short outline of my talk. So I start with a very short introduction about the main method that I use in my research. That is atomistic spin dynamic simulation. That is method that, among others, develops at Uppsala University at Department of Physics and Astronomy, and Ole Eriksson's group in particular. Then I will turn to the field of ultrafast magnetization itself, and to after these two results devoted to the coupled atomistic spin dynamic simulations of 3D ferromagnets, 4F antiferromagnets, and more complex system by ultrafast demagnetization triggered by the pulse of hot electrons in spin valves, including ferrimagnets. So let's start with atomistic spin dynamics. So this is a method that allows to consider various and study various magnetic phenomena on time scales, as you can see on the slide, from femtosecond to milliseconds, and on the system size scales from angstrom size to micrometers. And then you can study, for example, properties of skyrmions, which is topological spin structures that appear in ferromagnetic, antiferromagnetic materials that are very interesting due to their perspective as act for data storage, more dense and more energy efficient. Then one can study racetrack memories, magnetocaloric effects, permanent magnets, magnons, and the last but not the least, for me at least, ultrafast demagnetization dynamics. So a bit more detailed about atomistic spin dynamic simulations, or also now available atomistic spin lattice dynamic simulation, because for many magnetic phenomena, lattice dynamic is relevant and can influence magnetic properties. So in a code that we use in atomistic spin dynamic and spin lattice dynamic simulation, that is code that developed at Uppsala University. It's called UPSD, which stands for Uppsala Atomistic Spin Dynamics. And there we assume localized magnetic moment. That is code for classical description and is based on a magnetic or spin lattice, if you take lattice into account, Hamiltonian, which can include, for example, depending on your material, exchange interaction, magnetic anisotropies, the Alshinsky-Moria interaction, if you're interested, for example, in studying skyrmions, and so on. So parameters such as exchange interactions, magnetic anisotropy, and so on, in our code, you can use from either density functional theory calculations or from experimental measurement to describe the materials that you are specifically interested in. So when it comes to atomistic spin dynamic, then the dynamic is governed by Landau-Lifshitz-Gilbert equation that describe, as you can see here, the damped precessional motion of magnetic moment around the effective field given by your specific Hamiltonian. So if then we are also interested in lattice dynamic of the system, then we add lattice equations that are based on other atoms' displacements and atoms' velocities. So important also aspect of our approach that I will mention a little bit more later, that we can take into account also lattice, spin lattice coupling. So as you can see here on this figure in the right top corner, that when atoms vibrate, the distance between changes a little bit, which leads to small change of exchange interaction and to change, and this can in turn impact some system magnetic properties. So turning to the magnetic Hamiltonian, this can, for example, look like this, but of course it will depend on a specific system that you consider. So the magnetic contribution, exchange interactions, either from ab initio or from experiment. Then you have lattice with a force constant and magnetic atoms mass, and then spin lattice coupling that depend on these vibrations, so dependence of exchange interaction on atomic displacements. And then let me turn to the specifically main topic of my talk, to ultrafast demagnetization field. So ultrafast demagnetization was discovered in a pioneering work of Boris Pair in 1996. As you can see here, the initial demagnetization curve from their work. So what they observed, this magnetization quenching, magnetization reduction on a sub-picosecond timescales of thin nickel film following the absorption of femtosecond laser pulse. As you can see, so magnetization, sample demagnetized on sub-picosecond timescales, and then it's quickly followed by the recovery of magnetization on a timescale of several picoseconds. So on the top you can see some kind of typical schematic of ultrafast demagnetization experiment, of how they often call pump probe experiment, because your initial femtosecond laser pulse that you use to demagnetize your sample is followed after short time delay by your probe laser pulse, the second laser pulse, so pump probe experiment. So why are we actually interested in ultrafast demagnetization? Well, of course, it's interesting phenomena from the fundamental point of view, how fast we can manipulate magnetization, but that is also having very interesting and useful technical application, because if you look here, then in comparison with magnetic field, the manipulation of magnetization by laser allow us to manipulate magnetization on much faster timescales, which can be useful for future spintronic devices, manipulating magnetic memories and so on, which make it both fast, as we always want, and more energy efficient, which is also important. So yeah, one more scheme of the pump probe experiment from our collaborators in France that work on a so-called Bessie source in Berlin. So again, the source, the pump to demagnetize your sample, and X-ray pulse after this to probe magnetization after time delay. There is also possibility to apply external magnetic field, as I will show later why we are interested in this. So in this pioneering work of Boris Pair that started actually the field of ultrafast demagnetization, in addition to their experimental result that I have already shown you, and they're also presented here, they propose so-called 3-temperature model that is still very much used now, or used with some kind of modifications. So what they assumed to interpret their experimental results, they assumed 3 reservoirs with separate temperatures, so electron, lattice, and spin system, which have own temperatures, and then they can exchange heat, exchange energy via this spin lattice, electron spin, or electron phonon coupling coefficients. And then the dynamic of the system will be described by this set of coupled differential equations that are based on these coupling coefficients, as you can see, heat capacities of all 3 subsystems, pulse, of course, laser pulse itself is included, and the temperatures of electronic spin and lattice subsystems are also here. So what this allowed them to computate the dynamic of the electronic spin and lattice temperature and compare it with their experimental observation. And if we compare this simulation with the experiment, we see that they actually obtained quite a reasonable agreement. However, this model, in spite of its success and very much popularity, it has several disadvantages. First of them is that these coupling coefficients, they are quite hard to estimate. So even for 3D ferromagnets for iron, nickel, cobalt, they are in literature estimated with 1 order of magnitude difference from various theoretical works or from experiment, which make, of course, the comparison between theory and experimental data quite challenging. And secondly, it's maybe not very much visible here, but this model doesn't allow very good description of magnetization of sub-picosecond time scales. So that's why in our group we develop our own model, which has some common features with the trim temperature model of bore repair. However, we assume also 3 reservoirs, so electronic, spin, and lattice. We also have coupling coefficients between them, which are different. That is Gilbert damping, lattice damping, and spin lattice coupling. So the feature of our coefficient, they all can be calculated from density functional theory. But the main feature of our model, even not this, but the fact that we do not calculate our temperature in advance, but rather we measure them during our coupled atomistic spin lattice dynamic simulations that are already based on from ab initio exchange attractions, anisotropies, and all relevant parameters for the system as well as for the lattice. So then this measured spin and lattice temperatures, using the energy conservation, we can also calculate the electronic temperature. So turning to the results in first system that we tested our model at, of course, following the experimental observation of bore repair, who studied nickel, as you can see here again, his result. And on the left, these are results of our simulations that are the ultrafast demagnetization dynamic from specifically for nickel calculated parameters. And the blue and red curves here that are our heat concerning 3 temperature model, we call it, and the 2 curves that violet and yellow, those are bore repair 3 temperature model. So what you immediately see from here that our model provides much faster demagnetization rate on sub-picosecond timescales, which is more consistent with experimental observation in terms of demagnetization rate, as well as when the minimum of the demagnetization occurs and the recovery time. So one can wonder why there are 2 curves for each model. That is because following some other work in the field, we were looking on the impact of variable or temperature dependent heat capacities on the ultrafast demagnetization dynamic, because often in theory the dependence of heat capacities on temperature is overlooked here, but we showed here that it's quite important, especially if you look on a bore repair 3 temperature model. It changes the magnetization amplitude quite a lot and also remagnetization time a little bit. So on the right you can also see temperature dynamics from both 3 temperature model and our heat concerning 3 temperature model for various heat capacities. So what you can see here, the blue line is spin temperature, and one can see that in heat concerning 3 temperature models rise much quicker, so allowing much faster demagnetization rate, which is important for 3D ferromagnets. So following the quite positive results with nickel, we turned to iron and cobalt as a 3D ferromagnets. So on the left, on the left there is a result for FCC cobalt. On the right there BCC iron. So both on the bottom there demagnetization dynamic, again obtained of course from atomistic spin lattice dynamic simulation connected to heat concerning 3 temperature model. And on the top there are temperatures. So you can see that other 3D ferromagnets, they also exhibit quite fast demagnetization on just several, well, even within 1 picosecond after laser pulse. And that is consistent, as you can see on the top right corner, with experimental observation for iron, for example. Because if we consider this experiment for iron and we look on this black curve, that is this for the same laser fluence like we have in our simulations, and we have almost the same demagnetization amplitude, around 0.9 there, which is quite great agreement with experiment. Well, as I said already in the beginning of my presentation, our approach is great because it's allowed to take into account spin lattice coupling, which can be relevant for many phenomena when you study skyrmion dynamics, for example, for magnetocalorics, and for some materials for ultrafast magnetization dynamics. And so we calculated this spin lattice coupling tensor from density functional theory. And then on the right, you can see the result of this calculation, so ultrafast magnetization dynamic for iron with or without spin lattice coupling, which here, as you can see here, is only a marginal difference between them. So for, as we have seen for all 3D ferromagnets, spin lattice coupling is not that important here and doesn't play that major role. However, it can be for other materials, for example, for chrome iodide. So, but what I would like to persuade to that, even if spin lattice coupling is not actually that important, then taking into account lattice dynamic is anyway quite relevant for ultrafast demagnetization studies and to accurately describe experimental observations. And to demonstrate this, I turn to other experimental studies of ultrafast demagnetization in 3D ferromagnets, where they studied the demagnetization amplitude, which I show here with green, so how much you demagnetize your sample at given laser fluence, and they plotted this for various fluences for nickel, iron, and cobalt. And what they observe that demagnetization amplitude depends linearly on laser fluence for all of them. But interesting observation from this graph that in spite of quite different Curie temperatures of iron and cobalt, these lines are very, very close together in spite of almost 400 Kelvin difference between them. So we reproduce this in our simulation. So we also plotted this demagnetization amplitude as a function of fluence, as you can see here. So blue line, that is nickel, then iron is red, and yellow, that is cobalt. You can see that in our, if you look at this line, that our iron and cobalt, they're actually quite far away from each other. But if you look on these shaded areas, they demonstrate the range of this electron lattice coupling that are reported for the specific materials in the literature. So if we look on the border between these two areas, we see that lattice damping and or electron phonon coupling play important role in demagnetization, even if spin lattice coupling here is not that relevant. So we can find out the ratio between spin lattice couplings of these two materials, iron and cobalt, from here for finding areas where they're close together, like an experiment. Okay, so, but let me turn to from 3D ferromagnets to the next challenge, to ultrafast demagnetization of antiferromagnets. And that is also in our work, we follow the experimental lead. So, because antiferromagnets, we talked a lot already that ferromagnets and manipulate magnetization on very short time scales is useful for future memory devices, for read and write information, create skyrmions. One can also do this with laser pulse. But actually antiferromagnets are even more promising for future spintronic due to, for example, their robustness to external magnetic field. But also lanthanide-based antiferromagnets are especially interesting due to their quite big magnetic moment, which is good for technological applications. So in this work, published several years ago at Nature Materials, they studied the set of antiferromagnets, lanthanide-based antiferromagnets, that were created specifically to have very close to each other both magnetic structure and lattice structure. So their lattice structures have only 3% difference between each other. So the only difference between them is this magnetic moment of lanthanide material. But otherwise, they are very, very similar. So if we look then on the right, data results of their measurements. On the left, that is samarium-based antiferromagnet. On the right, that is terbium-based antiferromagnet. So what we can see immediately from these measurements is that they have very different timescales of demagnetization, from 5 picosecond around of samarium to up to 100 picosecond for terbium. And for holmium-based antiferromagnet, that will be up to 400 picoseconds, which of course make the comparison between them quite challenging. But what anyway was found out in this work, that quantitatively, these curves possess all of them the same feature. So demagnetization is always two-stage. It starts with a very sharp sub-picosecond drop, and then follow it by much slower demagnetization, as you can see maybe better at samarium demagnetization lines. So one more feature in this work is that the same as the experiment that I was just talking for 3D ferromagnets, they also looked on this dependence of demagnetization amplitude on laser fluence. And for all antiferromagnets that they studied, it's actually presented here. So they also observe this linear behavior, at least for up to critical fluences, which is in this work, critical fluence is definite as 50% demagnetization. So following this exciting experimental results, we decided also to apply our atomistic spin lattice dynamics simulations coupled to heat concerning 3 temperature models that we developed to these systems. And in this case, we actually wanted to quantify also the effect of lattice on ultrafast demagnetization dynamic. And therefore, we studied 2 cases, the whole spin lattice dynamic with a heat concerning 3 temperature model, and just spin dynamic with lattice completely excluded from consideration. So we have only electronic and spin system. So the results are for gadolinium-based antiferromagnet are presented here. So what we can see here, so first we obtain quite close demagnetization times for gadolinium. And also our curves, they also possess this 2 steps behavior. So first you have quite a sharp drop, and then it's followed by slower demagnetization. And if you look on these 2 curves on the top, which are blue and violet, so these are heat concerning 3 and 2 temperature model. So you see that they're very close to each other. However, this is observed for 3 times bigger fluences in the case of when you take lattice into account than if you disregard it. So, however, it seems like 2 temperature model, it can be, maybe doesn't describe the demagnetization amplitude of fluences that well, but it seems to be able, to reproduce main feature of a demagnetization curve. So we started following again experimental lead to look at ultrafast, this demagnetization amplitude from our ultrafast demagnetization curves as a function of normalized fluence, whereas critical fluence is a demagnetization of 50, that gives the demagnetization of 50%. So as you can see here, for all antiferromagnets that we studied using this heat-concerning 2-temperature model, without taking lattice into account, we still can see this linear behavior that is observed in an experiment. And then we turned to the lattice results, and when comparing here on the left case with and without lattice for gadolinium, rhodium, silica antiferromagnet, we see that they produce the same result in a good agreement with experiment. Okay, so I hope I convinced you that our model and our simulation can reproduce quite well 3D ferromagnets and 4F antiferromagnets. And then I would like to turn to more complicated experiments when you do not directly excite your sample with a laser pulse, but instead you excite it indirectly when the laser pulse is only used to generate the hot electron pulse that in turn demagnetize your sample. And in this case, we looked at this spin valve that include iron gadolinium, amorphous iron gadolinium film, that demagnetization we would like to study. That is scheme of the experiment from our collaborators, as you can see, in France, that performed this experiment on the Bessy facilities in Berlin. So first you have, again, this infrared laser pulse to trigger your demagnetization that is then absorbed in this layer, and you create the hot electron pulse. And then this in a cobalt platinum layers, your hot electron pulse is polarized, so you get this polarized hot electron pulse. And this allows in this experiment to look into different configuration when this polarization of hot electron pulse is either parallel or anti-parallel to the direction of magnetization of iron in the iron gadolinium. So here is a result of their experiment. On the left, that is iron contribution in this amorphous iron gadolinium film. On the time scales of the first 3 picoseconds on demagnetization dynamics, one can clearly distinguish between the cases of parallel and anti-parallel configuration with regard to the hot electron polarizations. So we see that in the case of parallel to iron, the sample demagnetizes faster, a little bit faster, and the magnetization amplitude is a bit bigger. And the maximum of this difference is around of half picosecond, as you can see on the graph on the bottom. So on the right-hand side, there are also, from the same measurement, the magnetization dynamic is up to 200 picoseconds for iron also, but one cannot distinguish after this due to noise is there any difference after 3 picoseconds between them. They also looked at the gadolinium contribution. However, as you can see yourself, it wasn't possible to distinguish between, is there any difference between parallel and anti-parallel configurations here. And there where we step with our theory. So we looked on this amorphous sample of iron gadolinium where we have areas more rich in iron, or areas 6% more rich in iron, or areas 6% more rich in gadolinium. And we have around 1600 atoms in our unit cell, as you can see, for example, here. And then we performed atomistic spin dynamics simulation coupled to 3-temperature model, and in additionally to demonstrate this effect of different polarization, we use spin transfer torque on top. So the demagnetization here is kind of combination of heat-driven demagnetization and spin transfer torque. And then you see the result of our simulation. So our lines that are simulations on the top of symbols that I experiment, both for iron and for gadolinium. And looking at the gadolinium, that was too noisy to draw any conclusion if there is any difference between parallel and anti-parallel configuration, then one can say from theory that there is small difference, less than in the case of iron, but it's still here. Okay, so I hope I convince you in my talk that atomistic spin dynamic simulation and atomistic spin lattice dynamic simulation are very useful tool to study various magnetic phenomena, that ultrafast demagnetization is very exciting field of research that also promise some future technological applications, and that heat conserving 3-temperature model is a great tool to describe ultrafast demagnetization phenomena in various systems, from ferromagnets to ferrimagnets, and that we can reproduce well the experimental observation. So the last thing that I would like to say, that if you're interested to use this atomistic spin lattice dynamic code of BSD, that is available for free on GitHub. You can download it, use it. There are also tutorials in the internet to get started. So I hope there will be new users after this talk from Ukraine. Yeah, thank you very much for your attention, and for organizers again.
Thank you very much, Maryna, for this very interesting talk. I certainly have one question at least, but I open for questions from the audience first. I think you were a little bit faster.
Sorry, maybe you have told about that, but I would like to repeat if you said about this. We know that in producing power, the more the frequency of the generator, the greater is the power produced. So the frequency of magnetization and demagnetization of the ferrum, for example, or other material is important. So whether your study is important for energetics, not only for spintronics.
For energetics, I'm not sure, to be honest.
Not just today, maybe.
Yeah, if these time scales are relevant, I honestly don't know.
Okay, thank you.
But that is interesting aspect, of course, to look at.
Maryna, thank you so much. Do you have any day? Okay, the summary, the lesson take home is that electron lattice and spin lattice interaction play different role depending on the type of magnetism of the system. What about altermagnets? What is dominant, if these interactions are relevant, important, and which was in the more dominant? Altermagnets.
Well, I never worked with altermagnetism, unfortunately, so it's hard for me to comment.
Okay, so that will be future.
That will be maybe future.
Yeah, you mentioned Ukrainians. There are 2 Ukrainians who work in Germany, in Dresden. Volodymyr Kravchuk and Konstantin Yershov, and they work now on altermagnets.
Yeah, I know that there is activity about altermagnetism here in Stockholm in KTH, in the group of Anna Derlin. So yeah, if you're interested, maybe you can contact her. But I'm unfortunately not a specialist.
Okay,
there.
Thank you.
More questions? Yes, Erik.
Yeah, thank you for the talk. I also take home I have from the talk is that the initial 3 temperature model, which you compared to, didn't work so well for nickel, right?
Well, in sense, it gives some insight, right?
Yeah,
and then
why
a
is
lot
that?
of
Why is
models.
that? Why does it work for the other 2 metals better than it does for nickel?
The problem that that I mentioned in the beginning, that with these coupling coefficients, that they are 1 order of magnitude difference if you look in the various literature sources, that's goes across all materials. So that is not just for nickel. They started with nickel. That's why we also started with nickel, and therefore we, in the first work on this model, we compared to nickel. But the same problem will go with the iron and cobalt and so on, that it's not fast enough. And yeah, that is especially relevant for 3D ferromagnets because they demagnetize that fast. Because if you look on terbium or gadolinium, where this demagnetization time around 100 picoseconds or further, then maybe you can apply it confidently. But also there are problems with energy conservation and parameters mostly. But what I like in our approach also that you don't calculate these temperatures in advance, which is basically accept heat capacity, they are not material based. And especially if you take like many also fixed heat capacities that doesn't depend on the temperature, then you get the same temperature profiles for any materials that you consider.
Yes, please.
Did you study maybe the influence of other nonlinear excitations that can exist in such systems like skyrmions, magnetic poles, solitons? How does it influence on the process of demagnetization?
So there are a lot of activities going on in ultrafast demagnetization to generate skyrmions and other topological structures using laser pulse. There was a lot of work on 2D materials, for example, chromium iodide, chromium chlor, when they generated by laser. So you observe this ultrafast demagnetization and then you generate skyrmions that you can see in these materials. Well, how they specifically influence the dynamic, there also, when you ask about solitons, I know that were observed following again laser pulse in iron platinum. But then they unfortunately didn't do any measurement of ultrafast demagnetization, so they see some lattice contribution. They have observed this in micromagnetic simulation solitons going on, triggered by this laser pulse. But then the magnetization curves, they doesn't reflect any difference in comparison to other work for iron platinum, where they haven't observed soliton. But maybe it was there.
More questions? Then I have an experimental question,
yes.
if you allow me. You mentioned that you have French collaborators
yes.
that are doing experiments in PESI, but they are using 100 femtosecond X-ray, circularly polarized.
Yes.
You need a free electron laser for that. So I don't understand how they can do it at PESI.
Well, that is more question
yes.
to him, to them. Yes, but I know. So that is this iron gadolinium work in nature. That is from our collaboration with these experimentals from France. But as far as I know, they did this in BESI source. So
I would have guessed rather at the European XFL, but there
well,
you can really.
I think it's BESI.
Okay. Yeah, we can find out. I was just a little bit confused by,
I think it was
by the fact that they should have...
Probably then they have. But not being experimentalist myself, I just believe them that they did.
Yes, I understand. Okay, I don't see any more hands. So let's thank Maryna again.
Welcome back from lunch to the afternoon session. We have 2 lectures, then a coffee break, and then a third and final lecture. And our first speaker is Ingemar Bengtsson from Stockholm. Please.
Okay, thank you. So I'm afraid there will not really be any experiments in this talk at all, except that it perhaps goes under the title of experimental mathematics. The physics side of my talk comes from quantum information theory. The number theory part, what you need to know about the number theory part, which is very much part of the motivation for the subject, is that this is a part of number theory that is not understood by number theorists, even though they've been working on it for more than a century. Anyway, the problem I'm interested in is that of constructing what we call a seek. So this is a definition. It's very simple. I can explain it to any undergraduate in 5 minutes. This is a problem. You're in a finite dimensional Hilbert space of dimension d. D always means the dimension of Hilbert space. In such a Hilbert space, you want to find a number, let's say n unit vectors that obey the following 2 conditions. They should form a resolution of the identity. There should be some constant there. And all their scalar products, mutual scalar products, should have the same absolute value. That's another constant. If you have such a thing, you call it an equiangular tight frame if you're in signal processing, etc. In quantum information theory, we call it a symmetric P of M. It's easy to show. I'm not going to do it, but it takes only, it's easy to show that the smallest number of vectors you can have in such a configuration is d, otherwise you cannot fulfill this condition. And the largest number of vectors you can have is d squared. And the case I'm interested in is the largest, the maximal case of an equiangular tight frame when you're looking for d squared unit vectors having this property. There are some good reasons for why you want such a thing. The original motivation had to do with various quantum foundational issues, but it has a number of engineering applications in quantum information theory. Such a thing in quantum information theory corresponds to some sort of generalized measurement. Having a symmetric, informationally complete P of M, a seek, is interesting in quantum state tomography. It's interesting in some cryptographic protocols, entanglement detection, etc. It's also of interest in classical signal processing. People doing theory of radar are interested in such things. Nevertheless, let me not hide the fact that although there are good reasons for being interested in this, it's not the world's most interesting thing in the world. What is very interesting about this problem is that it leads to an unsolved problem in number theory, and that's what I'm going to talk about. The history of the problem is as follows. It was originally raised by Gerhard Sauner in 1999, and then independently by Joe Reines and his friends a few years later. The interesting thing about it is that it's very difficult to find such vectors. You're looking for d squared vectors in dimension d. You sit down with paper and pencil and you easily do it for d equals 2. It's even easier in dimension 3. If you have the right idea, it will take you only 5 minutes to write it down. Dimension 4 starts to become more complicated. I'm told that Roger Penrose once did it in his head while attending a seminar. If you want to try that, I should also mention that Roger was looking attentively at the speakers throughout the talk. Dimension 5 is not possible to do in one's head, even if you have a very good head. Gerhard Sauner did it by hand, but he was guided by a rather deep understanding of the symmetries of these things, and he had to spend an entire summer vacation for the calculation. In higher dimensions, you have to turn to computers. In principle, if you write down these equations, these are multivariate polynomial equations for the components. You can try to solve them using Gröbner basis and a good computer. The problem is that when you write down the exact solutions for these things, as soon as you get to two-digit dimensions, the exact solutions, the actual numbers that go into these vectors, the expressions for them tend to cover an entire page per number. So they are really complicated numbers that go into here. The main conjectures in the subject that was made independently then by Gerhard Sauner and by Joe Renes and his friends is that these maximal equiangular tight frames, the SEEKs, they exist in all dimensions. They're also orbits of a group. I'll present the group on the next slide, not surprisingly. And once you know that, once you have a conjecture for what the group should be, you can do numerical searches for them. This has been done mostly by Andrew Scott, and they have verified numerically that they exist in all dimensions up to dimension 193. They always find them when they try. But these numerical searches are expensive. I mean, we're talking CPU years if we want to do it in three-digit dimensions. But it seems that they do exist. Here's a group that is supposed to generate the SEEKs. It's called the Weil-Heisenberg group. It goes back to Hermann Weil. The first book on group theory in quantum mechanics had this group. Julian Schwinger was another pioneer. There are various ways to describe the group. The usual way is to introduce two generators for the group. They act on the set of basis vectors in the d-dimensional Hilbert space. The index here is counted modulo d, of course. Throughout my talk, omega will denote the d-th root of unity. So you have these two generators that act like this. In theory of radar, you would refer to this as generating Doppler shifts and this as generating time delays, whatever. These generators are supposed to obey this relation here. This is the only non-trivial relation, and then they're supposed to raise to the power d, they're equal to 1. As shown by Weil, this group has a unique representation in a d-dimensional Hilbert space, which is precisely this representation here. The group has a very important property pointed out by Schwinger, namely that up to phase factors, you're going to have d-squared group elements, basically x times d raised to some powers, and then you can add phase factors in front if you like. So this set of d-squared operators form a basis in operator space, so any operator, unitary or not, can be expanded in terms of these operators. That's an important property. There's a bigger group hanging in the background, which is called the Clifford group, which consists of all unitary operators that permute the elements of the Weil-Heisenberg group.
Ingemar, where is Heisenberg coming into this?
Oh, this is because this group is actually, so to say, a finite dimension. Weil originally considered this group because it gave him, he was really interested in the Heisenberg's commutation relations, of course. He wanted to prove the Stone von Neumann theorem, that this has a unique representation up to unitaries. He was unable to do that. So what he did was he introduced this finite group as a toy model. If you write the Heisenberg commutation relations in exponentiated form, you're going to get rather similar relations here. So this for him was a toy model for the Heisenberg commutation relations. And then he was able to prove that this group has a unique representation in dimension d. So that's why it's called that. Actually, the group is much older, but anyway. Well, this is just a little bit about the group theory. I should warn you that if you look at Quant PH, you'll find the Clifford group appearing every day, new papers on the Clifford group. Usually they talk about a somewhat different Clifford group that is relevant for quantum computers. It's a bit different. Let me not dwell on that. This is a group which is actually more popular with signal processing than with quantum mechanics. Now we switch page, assuming we can do that, which we cannot.
Click on it.
I clicked. Oh, no, yes. Now, okay, so we have this group, and up to phase factor, it has d squared group elements, which I denote by dij. I and j run from 0 to d minus 1. And the idea is that you should be able to find a single vector, which is called a fiducial vector. You operate on that vector with these d squared group elements, and these d squared vectors will then form a seek. So you have to choose this fiducial vector in such a way that this relation holds. The constant that appeared in the previous slide has to be 1 over d plus 1. You can calculate that. So you have to find such a vector that leads to this relation. Alternatively, you can use a unitary operator basis property. You can try to expand this thing. So then you're going to have to fix d squared minus 1 phase factors such that this expression results in an operator of rank 1. So either you fix d minus 1 up to phase factors, namely d minus 1 complex numbers that forms a fiducial vector for a seek, or you have to find d squared minus 1 overlap phases such that this operator has rank 1 and defines a vector. And the question, as I was saying, is what are these numbers? How do you find these numbers? And as I was also saying, in the early days, culminating in a paper by Scott and Grassel, 2010, people actually solved these equations using Gröbner basis. And the exact expressions for them are absolutely scary. Well, that was a little bit too fast, but maybe I can go back. No, I cannot. Now I'm going to give the whole story away in 2 slides and then return to the details. It turns out that it's now believed, it has not been proved, that the key formula in the subject is actually this one. You take the dimension of the Hilbert space in which you want to form the seek, you look at this expression, and you write it in the form of an integer squared times a number which is square free. So it doesn't have any square factors in its prime decomposition. Then the following statements contain enough information for a number theorist to do the seek problem. This square-free integer that comes from this simple formula will define for you a quadratic number field. You extend the rational numbers by adding the square root of this integer here. The d, the little d, that defines the dimension, will then determine what's known as a Ray class field over this quadratic field. It's an abelian extension of the quadratic field. Okay, I'll come to the definitions later. And finally, this integer f that occurs in this formula will determine how many unitarily inequivalent seeks there are in the given dimension. So that's this slide basically tells you the answer to everything. It is believed but not proved. Using this information, one can actually construct seeks. This has now been done in these papers here. So there are explicit constructions starting from number theory that by means of which one can calculate seeks in very high dimensions, in dimensions that are much higher than you can even think of doing numerical searches for them. So in 5-digit dimensions, you can calculate the seeks using the information I gave before. So that's sort of the topic of my talk. And now I should give you a little bit of detail. And I will begin with a short course in number theory. An old piece of number theory that you probably know about. There is a problem in number theory that was settled in the 19th century, which has somewhat of a similar flavor, which is that of constructing regular polygons in the complex plane. You probably know that this problem was sort of solved by Gauss and others. So you want a regular, this is supposed to be a regular heptagon. It didn't become very regular when I drew it, but this is supposed to be a regular heptagon. And you normalize it by putting the origin at the 0 point in the complex plane, one of the corners at 1, 0, and then you ask what are the coordinates of the remaining corners. And as you may know, these already for the heptagon, these coordinates begin to look rather horrible. Here's the x and y coordinates for this corner in the heptagon. It involves cube roots and square roots and all sorts of things and complicated. So the exact solutions for 6 look like this, only just much bigger. Anyway, so this is how you brutally can solve for the coordinates of a regular heptagon. If you think about it, it's rather strange that such a formula exists. Because these numbers, these complex numbers, which are actually the roots of unity, obey this polynomial equation here. The roots, the 7th roots of unity obey this polynomial equation with integer coefficients. It's called the minimal polynomial for these numbers. And as you may know, it was shown by Aurell and others that in general you cannot solve polynomial equations of degree higher than 4 in terms of square roots, cube roots, etc. So there must be something special about this polynomial equation that allows you to find these solutions. And this was clarified by Sadi Carnot's contemporary, Évariste Galois. Galois said that one should focus on the group that permutes the roots of the polynomial while keeping the coefficients of the polynomial fixed. That's called the Galois group. And in this case, the Galois group is particularly simple. Suppose you have a permutation that throws, let's say, the corner omega to the corner omega cubed. But then omega cubed, of course, has to go to omega 9, which is equal to, because omega 7 is 1, to omega 2. So then if you permute this corner to this corner, then this corner will go to this corner. And omega 2 will go to omega 6. Omega 6 will go to omega 18, which is omega 4. Omega 4 goes to omega 5, and then it goes back to omega. So it's a cyclic group, an abelian cyclic group that permutes the roots of this polynomial. And Galois showed that if this group of permutation is abelian, then you can find explicit solutions like this. So this is why this happens. The story went on. So towards the end of the 19th century, Kronecker and Weber proved a very important theorem. They were interested in, okay, so this happens with the roots of unity. Of course, for any D, you get abelian Galois groups. The question is, what is the most general polynomial? What is the most general number field that has an abelian Galois group? And Kronecker and Weber showed that every extension of the rational number field that has an abelian Galois group is necessarily a subfield of such a cyclotomic field of roots of unity for some choice of D. That's the Kronecker-Weber theorem. There's, of course, even more that you know about the roots of unity, which is that there's a simple analytic function, in this case, this analytic function here, which is such that if you evaluate this analytic function at rational points, you get the roots of the polynomial. So that's a very satisfactory description then of all possible abelian extensions of the rational numbers. Now for the next century, the 20th, this started in mathematics with Hilbert formulating a set of problems that he, in his opinion, had to be solved during the 20th century. And one of his problems, the 12th, was to give a similarly complete description of abelian extensions with abelian Galois groups of arbitrary base fields. So you don't extend the rational number field, you extend some bigger number field with an abelian Galois group, and you want a similarly complete description of that. This was Hilbert's 12th problem. And the 20th century proved too short for this, so it's still open. In fact, the first partially open case, it's not because mathematicians haven't worked on it, it's just that it's hard. The first partially open case is if you choose the base field, the field you want to extend, to be a real quadratic field. So of this nature, first you extend the rational numbers by adding the square root of some integer, and then you try to find the most general abelian extension of this number field, and to give a similarly complete description of it as we had on the previous page. Now in the 1920s, Takagi, who was a student of Hilbert's, classified all the possible abelian extensions of this number field. And he called them Ray class fields, and they defined by something called the modulus of the Ray class field, which basically you choose any integer. Could even be an integer in the base field, doesn't necessarily have to be a rational integer. And okay, it's a sophisticated definition, but the really important point to notice is that all the properties of these Ray class fields, the most general abelian extensions of the quadratic field, can be obtained by analyzing the arithmetic within the quadratic field itself. So it's a nice example of how the tail wags the dog, in a way. So, yeah. The next piece of progress, this is not a very explicit description, he has classified what kind of abelian extensions that exist. So in the 1970s, Harold Stark made an interesting conjecture. He had a proposal for something that was going to play the role that the exponential function plays for the roots of unity. He conjectured that one could get the preferred set of units, as I called, in these Ray class fields from a certain, well, from analytic L functions. I'm not going to go into the details. It's a difference between two sophisticated zeta functions attached to, etc. Anyway, he had a definite proposal for a preferred set of numbers in these general Ray class fields, which would, if you could show that he was correct, would solve Hilbert's 12th problem for this particular problem, for this particular base field. And now we can go back to seats. Assuming we can. Yes. So in 2012, this is where the Seek story really starts. At that time, Marcus Grassel and others had produced exact solutions in about a dozen dimensions. They looked absolutely horrible. But Marcus Appleby, Julia Appleby, and Gerhard Sauner together analyzed these solutions, and they realized that in every case that they had available, these exact solutions consisted of numbers that lie in abelian extensions of a real quadratic base field, where the integer capital D that defines the real quadratic base field is connected to the dimension in which the Seek sits by this formula here. So there seems to be a definite connection between Hilbert's 12th and the Seek existence problem. This was taken a good deal further a few years later by Appleby, Flamia, McConnell, and Yard. McConnell is sort of interesting here because he's the first number theorist who becomes interested in this problem. They made a much more specific conjecture, analyzing whatever was the exact solutions that were around. They conjectured that in every dimension D, there's going to exist what they call a minimal Seek, for which the abelian extension is one of Takagi's Ray class fields, with a modulus chosen to be equal to the dimension. So this is a very specific conjecture. The evidence for it was rather slim at the time they pointed it out, but as soon as you have this conjecture, you can produce new exact solutions. You just take a numerical solution, you increase the precision a lot, and if you know what number field you're aiming for, you can use integer relation algorithms to deduce what numbers in that number field should correspond to the numerical solution, and then you can check it, and the number of exact solutions grew from maybe 15 to 100. So the conjecture seems to be correct. This accounts only for what's called the minimal seeks. An important development happened last year by Kopp and Lagarias, two number theorists. As I was mentioning briefly, there are typically in every dimension there are several unitarily inequivalent seeks, and they made a definite conjecture for the number fields that underlie every possible seek in dimension D. So there will be further abelian extensions of the ray class field that give more seeks than the minimal seek. So that's some of the background. And now let's see what's on the next slide. I wrote these slides some time ago, so I don't quite remember. Yeah, let me comment a bit more about what Kopp and Lagarias did last year. So it's sort of seek spectroscopy. So this is sort of experimental mathematics, as I was saying. So Andrew Scott, who is a very reliable person, believes that he has found numerically every seek in every dimension up to 90. And people believe him because he's a very careful person. And you see that the numbers of unitarily inequivalent seeks vary sort of irregularly with the dimension. Here are for the first, first there are a few low dimensions where it's unique, then there are two unitarily equivalent ones, and then here's 3, in dimension 15 it's 4, and then it varies. 35 is an example, then there are 10 unitarily inequivalent seeks, and it goes all the way up to 90. Now what Kopp and Lagarias did was that they said that, okay, let's look at this formula, which we had before. This is what determines the real quadratic field that underlies number theoretically the seeks. And they focused on this square factor here, which people have been throwing away as being not interesting because it doesn't have to do directly with the number field. Well, they were able to show that, to develop a further number theory to show that they developed a lot of number theory, let me say. And using that, they were able to predict that what you should do in order to predict these numbers here, all the way up to dimension 90, is that you should take this square that will appear here, you can easily calculate it, and then you look at the divisors of that integer f. And that will form a lattice of divisors, and that lattice of the divisor will determine the seek spectroscopy. So here's an example. Suppose the dimension is 35. You plug it into this formula, it's 36 times 32. You rewrite that as 12 squared times the square free factor 2, and then because of some stupid number theoretical complication, you also put the factor of 4 there. It takes about 10 minutes to explain why you put an extra factor of 4. And I'm not going to do it now. It's not so difficult, actually. So for 35, according to this formula by Kopp and Lagarias, you calculate that f is 12. Now f has the following divisors: 1, 2, 4, 3, 6, and 12, and they form this lattice, right? 2 divides 6, 2 divides 4, but 2 does not divide 3, etc. So it forms a little lattice. And the Kopp and Lagarias claim now is that for each point in this lattice, there exists a unitarily inequivalent seek. Actually, for 2 of the points, there exists because of a further number theoretical complication, which had actually been understood for some time. At this point, corresponding to f is 6, there are actually 2 unitarily inequivalent seeks. For f is 12, there are actually 4. If you now add up, it's 1 plus 1 plus 1 plus 1 plus 2 plus 4, it becomes 10. So it reproduces Andrew Scott's numbers here. And this works in 90 cases. 90 minus 3, the first 3 dimensions don't count. We start at 4. So in 87 cases, this correctly predicts the seek spectroscopy. This was sort of very exciting if you had been working on seeks for some time to see this. So it's from last year. I'm not very good at this, am I? Whoop. Now I'm going to explain what I was involved in myself, namely how you actually construct seeks. I was saying there were two constructions of seeks, where you actually start with number theoretical principles, you apply an algorithm, and you actually calculate these things. The construction I was involved in works only if the dimension is n squared plus 3 of that form. So it works for 7, 12, 19, etc. What's special about these dimensions is that in this case one can write down seeks that have an anti-unitary, the minimal seek will have an anti-unitary symmetry. This had been observed experimentally by Andrew Scott. It's easy to see why this should be so. But I'm not going to go into terribly much details. The point is that you analyze the symmetries of the seeks. If it is invariant under an anti-unitary symmetry, you can maneuver it by means of the Clifford group in such a way that it becomes a real vector. One of the seek vectors will be purely real, which is invariant under complex conjugation, which then corresponds to the anti-unitary symmetry. And then you apply a discrete Fourier transformation to the real fiducial vector. Using an argument which is actually due to Albert Einstein, who understood discrete Fourier transformation very well in 1914. He later became otherwise engaged, but in 1914 he wrote a paper that we rely on here. Applying a discrete Fourier transformation to a real seek vector, according to Einstein, results in a very special kind of vector where all the entries except one have the same modulus. So up to a phase factor you can assume that the seek fiducial vector is constructed from d minus 1 phase factors and one extra number on top whose size is easy to calculate from this relation here. So this, now according to the number theory, we expect that these d minus 1 phase factors should constitute a Galois orbit of a single number here. So if the number theoretical conjectures are correct, in order to write down a seek vector in dimensions of this form, all we have to do is to find one very special phase factor. Then we act on it with a Galois group to fill out the vector like this, and the result should be a seek, if the phase factor here has been chosen correctly. So the seek should be determined by a single number. And the question then is, what is this number? And this is where we turn to Harold Stark. Well, remember that Harold Stark proposed what's now known as Stark units. It's a conjecture, but he has a construction starting from some sort of glorified zeta functions, evaluating the first derivative of these, actually a difference of two such zeta functions at some specific point in the complex plane, and then raising it to e to this first derivative. That should result in a number which is an algebraic unit sitting in the appropriate ray class field, which should give rise to the seek. Such units, such numbers, are now known as Stark units, and strictly speaking, their existence in general is conjectural. What we find is that basically this number that we need to construct the seek is the square root of a Stark unit. There are procedures for calculate these Stark units, starting from these analytic functions. So we calculate the Stark units, we take their square roots, we put one of them on top inside the fiducial vector, we act with the Galois group, and we get the seek vector. Finally, we have to check that it obeys the seek condition, and it does. It does so in 80 cases. The highest dimension where we succeeded is 45,372. Which is absolutely impossible to reach with numerical searches. There are some complications, and this is a complication which so far affects all attempts to construct seeks. It turns out that this ray class field, which contains the seek somehow, actually has two branches for some reason. There is a real branch where every number in the number field is real, and there's a complex branch in which this is not true. The problem is that the start units live in the real branch of the field. So once we have the start unit, we have to apply a Galois transformation to it to take it to the what we call the complex branch of the field. And it's in the complex branch of the field where these numbers are phase factors. So the seek sit in the complex branch. And the problem is that this Galois transformation can be performed only if we have an exact description of the start unit. So you cannot use such a formula to calculate numerical approximations to seeks. You have to evaluate this number, this function here, to sufficient precision so that you can determine the minimal polynomial over the quadratic field whose roots are the start units. Then you can apply the Galois transformation. Having done that, you have to factor that polynomial, whose degree may be of hundreds. So it's a calculation. This is a calculationally heavy step here. An advantage with this procedure that we have here is that the degree, so the size of the polynomials we're talking about, grows roughly like the dimension squared. But it turns out that the fiducial vectors actually sits in a rather small subfield of the full field, which doesn't contain any roots of unity, so to say. They come from the Weil-Heisenberg group. So we work in this construction in actually a rather small subfield of the field that contains the full seek. That's why we're able to go to such high dimensions. Anyway, there is such a construction, and we can use it to, starting from number theoretical principles, we calculate certain preferred numbers in number fields that we believe are the relevant ones. Then we apply a procedure to these numbers, and we end up with what turns out to be a seek. And we tested that in 80 cases or so. Starting from this year, there is a more general construction available. I haven't fully digested the paper, which appeared in January, but it has 183 pages. And it's rather tough going. It's by Kopp and his collaborators, Gene Kopp. They aim directly for the seek overlaps, not for the seek vectors. But what they have is a fantastic function, much more fantastic than Stark's, I would say, which they call the Shintani-Fadeev modular co-cycle. That's a preparatory paper by Kopp alone, 50 pages, which explains the construction here. And using this function, they believe that they can produce, by evaluating it at specific points, so to say, they believe they can produce every seek in every dimension. They have the same calculational difficulty that I mentioned on the previous slide, namely that they do this in the real branch of the field, and then they have to transfer it to the complex branch, and that's a very hard thing, so they don't actually have any exact solutions. They have only numerical checks, but exact solutions have now been produced by using their procedure in 3-digit dimensions by Marcus Grassi. So there is, I would say, no doubt that they have the solution to the problem here in this paper. This is a general formula for seeks in every dimension. This function here, which they call the Shintani-Fadeev modular co-cycle, is a very interesting one. As you can see from the name, Shintani was a number theorist who worked on the star conjectures. Fadeev, you all know, Ludwig Fadeev. His name is here because this function that they use is also of great interest to physicists working, for instance, mostly in conformal field theory and related subjects. So they have to develop it a bit further. They have to do a lot of some various sophistications, but the roots of this function is partly from physics, which is also an interesting observation. Yeah, I guess this is all I have to say. I have one final slide. So we have these constructions by means of which we can calculate seeks from number theory. But there's one thing missing. In none of the papers I have been cited, that I have cited, is there any kind of suggestion even why this works. In other words, we have no not only can we not prove that the formulas or the algorithms that are supposed to give seeks actually work for any dimension except those that have been tested. And we have no idea really why they work. Yeah, sorry, this is a conclusion. We simply don't know at the moment, but that was it. Sorry.
Yes, we have a question.
I have a question. In what dimensions D do you have any applications that you could use?
Oh, in physics.
In what dimensions, I mean?
So the highest, so as I was saying, a C corresponds to a generalized kind of measurement. The highest dimension, and experimentalists have been quite interested in performing such measurements. They are optimal for quantum state tomography, etc., etc. The highest dimension in which anyone has really succeeded to make a good seek measurement is 3.
Okay.
My favorite dimension for applications actually has to do with the cryptographic protocol that well, it was mostly my collaborator, but anyway, I was involved in, is in dimension 4. There's a nice application to cryptography in dimension 4. Dimension 45,372. Now, I cannot predict, cannot suggest any definite application to that now.
But no dimension beyond 4 that you have an application in mind?
That depends on what you mean. In principle, if you have an unknown quantum state, and you want to construct a single measuring device, you have an infinite supply of copies, of course, of the state. You send it towards a measuring device. You don't change the measuring device. You just collect statistics. The optimal way to do this is using a seek. This is true in every dimension. But there is this little complication, of course, that you have to actually construct this device that corresponds to the seek. And as I was saying, the highest dimension in which anyone has actually done that in the lab is 3. Okay? You ask me next year, maybe it'll be 4. But okay. So it depends on how, in principle, they have very nice applications in every dimension. But if you want to be honest about it, it's not really true.
Okay. Thank you.
Maybe I ask one question myself. You said numerical solutions here.
Yeah.
Years to produce.
CPU years.
Yes.
Well, they run it in parallel, etc. But the total amount of computing time spent is typically CPU years, yes.
What roughly is it the one is doing?
Roughly speaking, you're looking for a vector. You apply once you have a proposal for the vector, you apply the Weil-Heisenberg group and see if you get a seek. So you do trials, right? You select the vector at random, you check it, if it doesn't work, etc. And then you have, of course, these things, I'm not doing numerics myself, but you have these gradient descent methods in order to improve things, etc., etc. It's a very sophisticated.
Yes.
If you try to do it yourself, I tried that. How Andrew can do all these things in these high dimensions is beyond me. But he can, there's no question. That is massive.
Yes, I don't doubt that it's hard.
Well, thank you very much for your talk. Could you please give some clue, some insight how this applies to, for instance, tomography? To build, may I guess, these vectors help to decide
if I had a blackboard, if I had a blackboard available, which I don't, I could easily convince you by doing a few scribbling a little bit on the board how to do it. Well, an unknown quantum state is a density matrix.
Yes.
A density matrix has d squared. It's a Hermitian matrix of trace 1, so it has d squared minus 1 parameters in it.
Yes.
A POVM, so a resolution of the identity, corresponds to a generalized measurement, which, if you have n vectors in the POVM, will give you n probabilities summing to 1, right?
Okay.
So if n is d squared, you're going to get, once you've collected enough data, you have a probability vector of length d squared minus 1. Same numbers as the unknown numbers, same number of numbers as the unknown numbers you want to estimate. So in principle, if you can perform such measurements and collect such statistics, you're going to determine the quantum state. Now the question is, suppose you don't have an infinite supply of copies, you only have a finite number of copies, and there will be statistical uncertainties in the result. The statistical uncertainties are minimized by choosing the P of M in this symmetric fashion that gives rise to a seq. It's something like this. It's actually not so complicated if I could draw some pictures, but I cannot.
You're a good speaker. Thank you very much. Yeah.
Thank Ingemar again. And our next speaker then is Liudmyla. I hope I pronounce it correctly. Derzhypolska.
Yes, it's correct.
From Kyiv.
Yes.
Please.
Good days. My name is Liudmyla Derzhypolska. I will present some key aspects about long-distance focusing of Gaussian beam. In recent years, our research team have focused on the propagation of laser radiation through the atmosphere. It's okay. Propagation of laser beam in free space. It's really important task in this world because when we talk about laser location, laser communication in free space. When we discuss about directed energy weapons and different most relation application, it's really important task in real world when we must understanding propagation of laser beam and take information about parameters when we must organize this good propagation beams. When studying the propagation of laser beam, we focused on special tasks. First, it's the geometrical focusing condition. In this moment, we discuss about analyze and optical schemes and focusing parameter in this scheme. Next important task is information about influence of the real atmosphere. Sometimes it's particular turbulence and difference moment when we through the beam atmosphere. In this topic, I stopped only first moment. It's about geometrical focusing conditions because next task is really big, and today I want to focus only first moments. When we speak about laser beam, we speak about Gaussian beam. Why do this task form in this situation? In general optics, before the lasers, we use ideal models. It's a plane wave. Ideal concept in the representation light with infinite wavefront, uniform amplitude, and no divergence. When we talk about spheric waves, it's more realistic waves, but it's still only approximately the behavior of light in specific conditions. But we speak about Gaussian beam. It's typical of electromagnetic wave, typical of laser beams, whose intensity distribution across the transfer plane is described as Gaussian function. It's sorry. In this simplest and most common solution of the Helmholtz equation under the paraxial approximation for light. Gaussian beam is the fundamental mode of laser cavity. Mode is the stable state of the electromagnetic field. Most electromagnetic fields inside optic cavity. When we talk about lasers, we describe about propagation laser beam in the cavity. The simplest type of laser resonator modes are Hermite-Gaussian mode, also known as transverse electromagnetics modes. In general case, Gaussian beam, sometimes it's ideal mode. It's fundamental mode of laser cavity. It's TM00 when the index N and M equal 0. I want to focus on some parameters important for understanding the propagation beam. Beam space. It's a point of minimum beam science. Generally, the beam waste is associated with focusing the beam. But it's next lection I want to special moment when we beams focus position in beam space at different moment and different aspect in propagation. When we discuss about beam quality factor, about relation rate, and about divergence angle, in general idea about means for how fast real beams propagation spread during the propagation. And most important parameter, it's beam radius and radius of wave curvature. This parameter described in the propagation waves during that axis Z. In general idea, we described only propagation in xz and fixed y and x parameters. When we talk about focusing of Gaussian beat at a local distance, we consider optical schemes as the outputs beams with radiation omega, beam radius omega, and wavefront curvature R. It describes. It describes the formula for beam radius square and wavefront radius. In general, we use beam radius square because in next formula and next parameter described in beam square formula. Parameter when we must understanding what the beam propagation in long distance we in focusing system we described and maybe focus on moment when we beam create a beam waste. Sorry. create beam waste and a special distance Z1. General idea is focusing beam must be create beam waste and it's a special focus, special optics scheme. Beam waste create an point when describe optical system and the focusing system when we use in this optical scheme. Continues analyzed our equations taken previous slide. We focused on a specific moment when the right. It's right. Parametric dependence. It's first dependence of beam waste omega 0. It's described on wavefront curvature radius and parameter Z1 the same described in curvature radius, and we talk about its analyze special parameter. It's omega 0 on Z1. Why we analyze this moment? Because when we describe this parameter, we take about information minimum radius when we can formation this optic scheme and place when we beam waste will be formed. For plot this graph, we use special parameter. This parameter is described real experiment scheme when we use in our work. Investigation Z1 on wavefront curvature radius for the extremum was obtained maximum value of the distance to base value of this distance. When we must, when we can formate this omega 0, when we real size for omega 0, and 2 it's maximum when we can formate its wavefront curvature radius. Finding omega 0 on Z1 leads to the consideration of the square equation, which has two solutions. This solution is described in this graph and position. One position in and 1 and 2 position in this graph. Continue of our research. We focus on of Gaussian beam over long distance more than 1,000 meters. When we discuss about beam space, we means about position which can form only one place, and real systems which formed as beam the spot minimal spot diameter. It's sometimes important form, it's special place. It's not the same place when this can form beam waste. Consider the behaviors of the focusing beam after the base at this distance Z2 greater than Z1 max. Z1 max its position when we can form beam waves in this optical parameter, our scheme. And analyze this formula when we take in using this beam waves and position position Z1 with previous slide we plot the graph and we can see at minimum. For a particular value of wavefront curvature radius r, the beam radius omega 2, its distance Z2 becomes minimum. Its initial, the most common compact beam is this distance. Important moment in this, when we plot this graph, we fixed position Z2. Its position equal it's 1000 meter. For understanding which is propagation laser beam, maybe we want to create a minimal beam spot in different place. It's not only one kilometer, it's maybe big length. We analyze of position and analyze this formula for different position. For different Z1, the minimum of graph omega 2 on wavefront curvature radius plot on standing line described formula in this. What we show? We show a special moment that when we analyzed its minimum, this graph, ideal minimum diameter when described in this formula for different Z2, we create a line. Sorry, it's not line. We can achieve the smallest position beam diameter at a remote position Z2 by currently choosing the wavefront curvature radius to match these two. In comparison of minimum spots and beam waves. For more clarity understanding this moment, we described some condition when we form this beam spot and beam waves. First, when we want to create a minimum spot size, generally we have idea it may be a beam waste. Okay, we have a optical scheme, standard optical scheme, which standard for optical scheme, which can form beam waste on position Z1. Okay, when we want to form minimum spot size in distance Z2. Okay, when we take in this the same optical scheme, we can't form this beam space. but we form special maybe it's maybe a minimum diameter of beam when we propagation using this scheme. Next point, when we can in this moment maybe we change in our optical scheme for formed beam waist in position Z2. Yes, we can't, but when we form a new optical scheme, we formed a new wavefront curvature radius. We formed a new different parameter which increase beam waist. In this moment, we understanding its minimum spot size for point Z2. It's different means when we formed beam waist. For more understanding this moment, we analyze this formula 2. It's described in a beam waist in general case. Analyzed some position in this show on this graph. For position, for distance, maybe it's area when lambda Z1 less than omega 2. What we show? We showed becomes the same the optimal focusing. 1 minute on this. But we analyzed in next place. It's about more 1,000 meter. We have difference plot for minimum spot size and for beam waist. And it's important moment because when we create a real systems, in general means we used a formula for described beam size, and real systems not good to describe this moment. For very few our results, we take its experiment. We conduct the next experiments. We analyze the same optical scheme. It's focusing our beams on distance Z2. We can change this focusing place, choosing in condition for using the O1 and O2. On1 in our scheme was micro objectives, and O2 it was magnitude of lens. Next moment in this, it's focusing in this position and state its screen and take information about beam diameter on the camera. In this photo, it's a real experiment when we provide in our institute. Next one, I described more this experiment. I want to focus on a special moment. When we provide this experiment for analyzed beam diameter, we must using its special methodology. For us, we use and described this experiment. It's ISO standard. It's a general ISO standard for describes the methodology of laser beam width, divergence angle, and beam propagation relations. Come back in this position because some moment I want to describe in this method. This ISO standard, it's more important because when we show our beams on focusing distance, it's this. We can show its real photo is this moment in video. Beams, it's really not state and have different different moment in focusing position. But we use this method for described. What is first moment when we used? It's beam diameter described. It's therefore sigma with the corresponding. It's 18.5% of the total power of Gaussian beam. It's a general idea when we use this ISO standard. We analyze the focusing beam diameter. Next step in this, it's use its second order moment for describes intensity distribution when we take information about beam diameters. And use its principal axis when we marked center of this diameter. It's two moments, and one certain moments in this calculates this data. It's use iteration algorithm for described place with described its beam diameter. It's this method help us for for understanding. Or maybe it's take its correct position for beam diameter, calculate of sides of this diameter, and analyze this data. Our group create or program create program when we which can analyze its beam diameter in real time, because when we watched this diameter, we can understand it's minimal, but it's not minimal. But when we complete this information about diameter, we choose a special application. It's this method include its first step. We use program for correct choosing beam diameter, and next it's recorded 5 frames for pre-exposure and different place. what is this slide? It's our results. We analyze its laser beam on this distance of up to 25 meters. With step of 50 meters. In this graph, analyze its green laser, and this we analyze its red laser. It's 1632 nanometers, and this it's 1532 nanometers. Was described, was calculate average diameter and beam size value described linear dependence over the all distance. But when we remember about information for the same size of beam base and minimum focusing beam. Next experiment, it was choose distance for 1,000 meters. We proved our experiments on standardized track in with 1,000 meters. And what we show it's good include sorry, it's my mistake, it's 1,000 meter point. The deviation between the extrapolation and experiment value is significantly smaller than 3 sigma. It's we show it's the line plot in this situation. What is highlight idea in this work? It was theoretical and experimental confirmed that the best focusing condition correspond to the minimum spot, which does not coincide when the beam plays. The minimum beam diameter exhibit linear dependence on the propagation distance, whereas the diameter of beam base changing non-linear with the distance. The minimum spot site is described as the following formula. This formula it's describe only minimum beam sites and describes beam based on position when we have distance more than 1,000 meters, less than 1,000 meters. And it's a good idea to use the ISO standard for processing experiment data on the minimum laser spot diameter. In the end, I want to share some photo with our field experiment. For me, it's more important than this photo. It's show standardized track. It's really one thread in Ukrainian which have errors of 1 centimeters on 1 kilometers. It's a real standardized track. But this track was stayed in Kharkiv region, village Lviv. Now it was destroyed Russian terrorist. Sorry. And I want to talk in this situation. We can stop the work in general situation in Ukraine and continue our work for help, maybe arm, for help different people. Thank you. Sorry.
Thank you, Liudmyla. Questions?
Sorry, my question is general. Your nice results will be the same if we'll carry on your experiments in vacuum, or atmosphere does influence?
We provide the experiment with atmosphere, and maybe I sometimes remember it's my results. When we talk about in graph, it's a graph in it's characters signs of the beam diameter. When we show in 1 kilometer, its character size, it's 15 millimeters. And from that, it's real results. What we show it's 1 kilometer. We have size 15 millimeters. It's atmosphere effect when we watching this.
And what parameters are?
Yeah, it's special parameter when used. In this presentation, I don't focus on this moment, but we provide this work and take a special experiment. It's important to for affect atmosphere on this distance. It's have a problem for calculate, because it's turbulent effect on this distance must be no, what is get for special functions must be described as special functions.
I remember a long time ago when I did experiments with lasers that if we had a Gaussian beam, we were happy and we could start the experiment. If we had a donut beam, we were unhappy and we didn't start the experiment. And I guess that, I mean, now you in your analysis you have
Yes.
treated the Gaussian beams.
Yes.
But if, let's say, you had some of the other modes, it would perform much worse, I would assume.
When we in this experiment was provided its green laser is DPSS laser with m square equal 5. It's not good Gaussian beam, yes. But general Gaussian beam is m square equal 1. It's laser for maybe for science. When we use in this task, laser have problem with good equations, good parameter for beam parameters.
Yeah. I'd like to continue the first question. Is your medium linear, or you take into account the influence of field in a beam on the medium, non-linear effects?
Non-linear effect it must be included in turbulence.
Into
turbulence. Okay. It's affect atmosphere. In this, I don't include in my experiment data.
It's taking account phenomenological.
Yes.
What do these techniques used for military applications too, in the war?
Repeat, please. I don't hear you.
these techniques that you describe, are these used in the war?
This text.
To focus
Техніка в війні використовується. I will translate. Okay. Чи використовується ця техніка в військових застосуваннях?
Its techniques used only for science now. It's a methodology for research our groups, and maybe it's more application in ARM, and it's different task, but it's general. It's only science.
Sorry, this is not a question, but an answer to you that in Ukraine there is created the laser weapon. It is announced in public.
Yeah. No, I read in media that Ukrainian military are very creative, especially with the drones, and I suppose these techniques can be handled by them.
But that is the closest information except the general description. We don't know the parameters, we don't know type of lasers, you know, but we know that that's used that for.
Yeah. It was only science task, only. Because I can provide, I can share this information in this conference.
Yeah, obviously. See no more questions, so let us thank Liudmyla again. Time for today's final talk. It's a pleasure to welcome Larissa from Kyiv.
Thank you. Well, dear ladies and gentlemen, dear colleagues, and I should say, dear friends, this is my real pleasure and honor to give this talk here, especially in this audience. And as you hear, I am excited, I am nervous a bit, and unfortunately I have very bad feeling of time, so I asked Mr. Chairman to warn me 5 minutes before the talk, because the talk is rather general kind of the overview of the history of the wave of translation, or soliton as we say, and 50 years of the Davidov soliton. I'm from Kyiv, from the Bogolyubov Institute for Theoretical Physics, so I am a theoretician. We do theoretical studies of nonlinear processes in condensed matter systems, in biophysical systems as well. But before I proceed to the scientific part of the talk, I think that's my great desire and my duty to thank the Royal Academy of Sciences, in-person Professor Larsson, Professor Aurell. No, this all started Anders Irbak, sorry for wrong pronunciation, for organizing this meeting, this event, and this collaboration, I should say. There were two things just from the blue. The first thing was visit of these two guys to Kyiv in the period of the full invasion of Russia in Ukraine, of the power shortcuts and cold weather and so on. They came here. All people were trying to live in the opposite direction. And they said, no, we go against the flow. And the second scene from the blue sky was the visit here in Stockholm, and not simply to Stockholm, but to this outstanding place. So really, thank you so much. So I decided to speak, as I told you, about the general things, solitons, solitary waves, and particular type of them in biological systems. In the end, if I have time, I will tell you the recent original results on the study of the impact of oscillating magnetic field on soliton dynamics, since this has also important applications in technologies and in medical applications. So now practically everybody knows the term soliton. How they were discovered? Officially accepted 190 years ago, but as I will convince you, even a bit earlier. Since the first of all, the 20th century became the century of the quantum physics. And the second half of the 20th century became the physics of nonlinear systems and quantum nonlinear phenomena. Soliton. The general definition of the soliton is that this is a special class of the solutions of the wave equations. In mathematics, they say of complete integrable systems. It can be discrete, continuous, differential, integral differential equations. This particular type of solutions which possess the following features. They are solitary, so they have only one maxima of the wave in their distribution. They are stable, they propagate with the constant velocity, not losing their amplitude and velocity, and when they interact with each other, they don't change their properties. So they are waves, but they don't interact like ordinary waves, or we say linear waves, but rather like particles. And this feature is reflected in the term soliton, almost like electron. There was intention to call them solectron, but at the time when the term was introduced, there was a company with this name Solectron, so that was the change. So how it has started? In 1834, Scottish engineer, scientist, architect, shipbuilder, John Russell Scott observed the particular, very specific wave in the canal near Edinburgh. And that's officially accepted as the discovery of the soliton in scientific literature. But it all started a bit earlier. According to my knowledge and what I could find in the literature, the first known description of the solitary wave is dated as far as 1820, 14 years earlier, and belongs to Italian engineer, mathematician, hydrodynamic experimentalist from Turin in Italy, Giorgio Bidone. He published a paper in 1820. This paper was translated into English. It was mentioned in the Edinburgh Journal of Science in 1826, but the very description of the soliton, of this nonlinear particular type of the wave solitary, was left behind any attention. There were other aspects mentioned in that references. How it all was discovered. The easiest way of traveling in Scotland was traveling by light, flat-bottomed vessels along the canals, which are very numerous in Scotland, maybe even less than here in Sweden, but nevertheless. And these light flyboats were drawn by horses. For instance, some of the pictures I have taken from Wiki shows this canal still exists near the mill. These flyboats were pulled along the shallow water canals. Those who do nonlinear physics know that shallow water possesses some peculiar features and the equations and so on. And one day, an employee, or some other sources say that he was the owner of the flyboat company, was traveling down a canal, and he observed, he saw that one of the forces pulling the flyboat was startled by something, bolted. Well, William thought that the horse soon will stop, but it did not. So he watched what's happening further, and he was amazed to see that the boat, which stopped sharply, abruptly, rose up onto the wave formed under its bow, shot off along the canal at the high speed, and there was something very strange. The water exhibited no resistance to this flyboat. And furthermore, there was no turbulence near the shores of the canal when the water reached, the wave reached this. Now we know this as hydroplaning. And many people, some people do this in their... there is a nice story, Daringol, the spirited horse. We will see why this horse was spirited. John Scott Russell, the shipbuilder, he read about these strange phenomena that water shows no resistance to the flyboat, and we thought, well, maybe I can study these phenomena and get some ideas how we can improve the boats, the barges to carry coal from the mines to the shores in Scotland. And he read more on this stuff, and then started doing some experiments. And in parallel to these, thermodynamics worked, because at that time he studied also the possibility of transition from the horse-driven power to the steam power engines. So he was watching barge going on the canal carrying the coal. And again, the horse helped to discover some particular very interesting phenomena. The horse, the boat sharply stopped. There should be the waves, of course, created by the boat, by the barge which stopped in the water. But what's happened at that time? There was one big increase, one big wave with one maxima in front of the boat. The boat stops. This wave leaves the boat, barge, and propagates along the canal. First, this canal with parallel shores, and then goes into the natural part of the canal. Strange enough, in this conservative country, this canal still exists. It's exactly this canal. And he saw that the wave propagates, does not change its form. doesn't change its speed. He first walked, then he decided, no, I have to see how far it goes. So he took a horse. And as he later wrote, it was the happiest day in his life. And he wrote about this observation. The article described all main features of solitons, and even there was a special committee organized by Edinburgh Society to study these processes. He built a tank in his yard to study experimentally these waves, and so on. That picture, I can show this without the reference to any sources because I have this picture as well with my camera. That happened in 1995 when there was the conference in Scotland, and it was the second conference when scientists decided to relaunch this solitary wave in the same canal where it has been discovered. The first time in 1990, the experiment failed. The organizers decided that maybe the boat, the boat with electric engine, maybe it was not enough powerful. So in 1995, they took a powerful engine. The boat comes into the aqueduct, suddenly stops, abruptly stops. No solitary wave, no solitary wave. There is a disappointment, and I say, well, it's not only the power of the boat, but it's also the weight which the boat carries, because that time it was the boat with the coal. I told that because I did mathematical exercises, I should say, the inverse scattering method with the nonlinear Schrödinger equation, looking at the time and special evolution of the initial excitations. And I knew that creation of solitons requires special conditions. But I was I was standing near Elvin Scott. We will mention his name later. He is here in the wheelchair. Elvin Scott is known for his review paper on solitons in different systems. And young boys, students were standing next. They heard me speaking not very loudly, much lower than now. And they rushed to the boat, embarked on the boat. I didn't expect this. You know, I am a theoretician. I can't predict this. My heart sank. But with the first attempt, the boat with students on it entered the aqueduct, stopped, and that beautiful, beautiful solitary wave was formed and passed. It was not also smooth because in the beginning there was the kind of the resistance to John Scott Russell discovery. He described this as the wave of translation. Then it became known as the class of the running waves or solitary waves. John was not a mathematician, although he gave beautiful lectures at the university and these lectures in Edinburgh. And these lectures attracted the biggest number of listeners at that time. So there was some critics. But then some as I say here at the beginning, we know names of George Airy, George Gabriel Stokes, known for his Stokes equation, they were opposed to this, but then, including the George Stokes, changed his attitude. And the crucial transition point was in 1872, when Joseph Valentin Boussinesq derived the equation which is known as the Boussinesq equation. And I want to cite the first sentence of his paper. Unfortunately, I don't speak French, so I couldn't pronounce it so beautifully as Erik did, but the English translation says, young boys here and girls, all engineers know about beautiful experiments of John Scott Russell and Bazin on generation and propagation of solitary waves. So that was a crucial transition. Then the next step was in 1895, when Diderik Korteweg and Gustav de Vries extended the Boussinesq approach and derived Korteweg-de Vries equation, which is simpler to study, and it shows the existence of the solitary soliton solutions. The next step, the milestone in this studies was in 1955. In 1955, it was the birth of the new field of research, the nonlinear science, and it started with the problem which we now call as Fermi-Pasta-Ulam problem, but in fact it should be called Fermi-Pasta-Ulam and Tsengu, because all the experiments, the first computer simulations were done by this beautiful lady, Mary Tsengu, who married Menzel and then had the name Menzel. And that was about the semmelization of the system crystal, to study how crystal evolves towards thermal equilibrium. So the simplest model was the chain of particles linked by linear, as we say, interactions with weak nonlinear additions, and they observed the absence of the semmelization and formation of the solitary waves solitons. And in 1965, finally, the term soliton was invented by Zabusky and Kruskal. So soliton, I remind you, a localized solitary wave, which is solution of nonlinear equations or equation which does not change, solution does not change its shape and amplitude and velocity under interaction with each other. In 1973, Elvin Scott, Chu, and McLaughlin published this paper in Proceedings of IEEE, which became a very known review paper. And at the same time, in 1973, Davidov, we can see him on this photo, he worked on excitons in crystals, in solid-state systems, and he was very well aware about the role of collective modes and that they can lead to the appearance of totally new features, the emergence of novelties, I should say. And he heard about the problem of crisis in bioenergetics. I don't know if I will speak about this later. On the what do I show? Yes. So I come back to this. So in 1973, the first paper was published, done by Davidov and his PhD student Mykola Kisluha on this picture. And they showed that in one-dimensional, quasi-one-dimensional molecular systems, when we take into account electron-lattice interaction, the solitons can be, soliton solutions appear. And they are efficient carriers of energy and charge in such one-dimensional chains. Elvin Scott visited Davidov, that is that is in the seminar room, and that was probably in the yes, that was in the office, Davidov office, who was at that time director of the institute, of Bogolyubov Institute. So, what was the problem? We know that in biological systems, the elementary and the main unit of energy is the energy which is released in the ATP hydrolysis reaction, ATP to adenosine diphosphate into adenosine 3-phosphate. But this energy is very small. It's less than half electron volt, which is comparable with the thermal energy of thermal excitations at the room temperatures, about 20 kT. And this energy is released in one place in the biological cell and is utilized in another part of the cell. So this energy has to be transformed with high efficiency from one place to another place on the large distance at high temperature. And no available mechanism could explain this efficiency, and that's why the annual meeting of the New York Academy of Sciences in their concluding notes wrote that the bioenergetics faces the crisis. We can't explain this. So in parallel to this, Davidov was working with Kislucha, and Davidov said, well, this energy propagates in the biological cell, not in the vacuum, not in the atmosphere. The cell is tightly populated. There are many macromolecules, as we say, which possess the crystal-like structure, like Viktoriya showed us, for instance, this one-dimensional polymer chain. And this macromolecule structure plus collective electron states in these structures are very crucial. And what was the genius idea was that biological macromolecules are soft. They are kept by relatively weak hydrogen bonds. And weak bonds means that the electron-lattice interaction is very important, even more important than in the magnetic systems, as Maryna told us in the first half of our meeting. So they derived the system of equations with electron-lattice interaction taken into account, one-dimensionality, and the solution was this soliton. We will see it later. So Davidov, in his book, Solitons in Molecular Systems, wrote that nonlinear states are as fundamental as are quasi-particles in linear theories. So the model is very simple, just on the fingers. There is, these two figures show the top and side view of the protein structure. We see there is helical chemical bonding along the polypeptide chain. Along this chain, we realize that there are three chains formed by first and fourth peptide groups, which are kept bound by the hydrogen bonds. And the interaction between the three chains are rather weak. So they decided we take the simplest model as we often do, but not linear model, non-linear in the sense that we will take into account the electron lattice interaction. So these dots show a hydrogen bond. The black dots are peptide groups. There is displacement of peptide groups from their equilibrium position induced by excitation, and this excitation is the energy which comes from the hydrolysis of the ATP to ATP molecule. And from the point of view of physics, we have the system which is described by the Hamiltonian, which consists of three terms: electron part, lattice or phonons, as we describe lattice in terms of quantum physics or solid-state physics, plus the term of their interaction. From these equations, we derive the system of coupled discrete equations. We can apply the continuum approximation looking for smooth solutions, and in the continuum and adiabatic approximation, from this Hamiltonian, they derived the nonlinear Schrödinger equation. Here we see the nonlinear term, psi cube. Psi is the wave function of the excitation. There is important parameter here, the nonlinearity parameter G, which is proportional to the square of the electron lattice coupling, inverse proportional to the resonant interaction between nearest molar peptide groups and the elasticity of the hydrogen bond of the chain. And that's the well-known soliton solution. I have to show you it, although everybody knows. This is in hyperbolic cosine with the amplitude and width determined by this nonlinearity parameter. And later, this excitation, this solution was called by Elvin Scott Davidov soliton. So the energy released in the ATP is stored in the vibration, which is called amide-1 vibration, which is basically the vibration of double carbon-oxygen bond, chemical bond. It interacts with the lattice. They form together a bound state, and in this bound state, they propagate excitation plus electron, plus lattice displacement. They propagate from one side where the soliton was created to another part and carry with probability 1 in this idealized case, they carry the initial energy from one terminal end to another terminal end. Later, this model was generalized to explain also electron transport. In living systems, electron transport takes place in redox processes, and redox processes accompany our respiration, photosynthesis. It all occurs in the electron transport chain in membrane of the mitochondria, shown here. This membrane, in this chain, there are enzymes of different types. Some of them, shown on this figure in blue, have small mass, and some others have large, big molecular mass, and they are in the, almost 90% of them are in the alpha helical conformation. And during these redox processes, two pairs of electrons or electron pair is created on the one end of this chain and is gradually transported from along this chain, not like this shown by this dotted line as the picture taken from some book, but gradually from one enzyme to another enzyme and so on. And in the end, the electron pair forms the, as they say, half of the water molecule. We don't say, we say two pairs of four electrons form electron bond. So the situation here is similar to the molecular excitation. Electron deforms the chain, and this self-created deformation works as the potential well. It attracts electron, and together they propagate in the bound state. When we speak about electrons, their statistics is important. The statistics and, of course, the Coulomb interaction. So when we take into account spin of electrons, we concluded that the singlet bisoliton can be formed in the chain when two electrons excuse me, form a bound state. They form the same potential well with one minima, and this potential well attracts thank you so much. I told you the time goes fast. Okay. So they form the bound bisoliton state. If the spins of electrons are opposite, they form a triplet state, which has different energy, and so on. When we speak about solitons, the parameters, the geometrical structure is very important. The class of solutions can be big, and the solitons, different solitons possess different energies and different temperature stability. Like, for instance, in helix, there can be different solitons. There are the experimental evidences of soliton existence. These molecular solitons exist not only in biological macromolecules, but in organic polymers, in superconducting polymers in many quasi-one-dimensional systems. There is a large class of novel materials which are used in the biomimicry technologies today, so that problem is still very important. So the class of donor helix or donor chain acceptor systems admit this effective transition in the form of the solitons. This shows the soliton in these polymer chains, our numerical simulations. I skip here. The experimental evidences on the measurement of the lifetime in the system with the same primary structure, the same L-alanine molecule, but which have different secondary structure, like alpha helical polymer of myoglobin, or beta sheet yellow protein, and lifetime is totally different. There are evidences of the soliton input into the delayed luminescence of the biological systems, and in this theory was the first to predict not only qualitative, to provide not only qualitative description, but also quantitative description in a wide range of the parameters, and some other experimental data. So the last part, which I have to skip, is the impact of the magnetic field on the soliton provided transport in molecular systems. And this impact has a non-thermal resonant effect. So it shows the importance of the magnetic fields. The impact can be positive or detrimental, and explains the mechanism of the therapeutic effects. Well, some insight into the into the physical mechanism of the therapeutic effects of the. And I expected to speak about all this, showing so many. Fantastic, Larissa. Of course, there is enough time. So, the impact of magnetic field depends on the orientation of the magnetic field with respect to the molecular chain, the resonant character of the impact, different changes when the field is constant or when the field is oscillating. I would not recommend to use, for instance, tomography without any special need, because that exposure to the, and it's not only a question of the intensity of the field, but the question of the frequency of the field, the same about the our mobile phones. So I have to shut down, but still. Thank you so much. Thank you, Swedish people. And thank you, Armed Forces of Ukraine. And thank you very much, since I'm the last speaker, thank you very much to all participants, to everybody who came. Thank you so much for the organizational assistance to Peter. Thank you so much for the computer presentation. Thank you all. Thank you, dear Mr. President.
But maybe there are questions for Larissa. Not?
Yes, Larissa, do you think in all this formalism with solitons in biological molecules, would there be any way of detecting a difference between chiral forms? I mean, in other words, the L form of a polypeptide and the D form. Is there anywhere where you can think about that would be a difference?
Yes, the difference will be when we take into account the helicity and when we speak about, in my opinion, when we speak about the electron transport, about the spin, then the difference will be important. Yeah. But at the moment, to show this on the formula, I can't. But definitely.
But the electron transport, that would be this type of experiments done by Ron Naumann in Weizmann Institute, I guess.
Yeah.
I remember that Alexander Davidov very often stressed that it is very important for certain solution to have one-dimensional case. And what about two-dimensional, three-dimensional case and solitons? What is the situation?
That's a very good question. Thank you so much. We applied this theory to the, I will try to be short, brief. We applied this theory to explain the first superconductivity in low-dimensional organic systems and then in high-temperature superconductors. And I gave a talk at the general meeting of the Academy of Sciences, and they told me, no, Larissa, we know that the solitons of the nonlinear Schrödinger equation are not stable, are unstable. They shrink in the 2- or 3-dimensional systems. That's true, but physics is much more rich than mathematics. In physical systems, there is the restriction, which is the discreteness of the system, and that's the question of the parameters of the system. Because soliton solution depends on the values of the parameters. Some initial excitations can create solitons, some others not. At some parameters, for instance, in close, identical by the structure systems, but with different electron-lattice interaction coupling constants and other parameters, the soliton cannot exist. So there is no restriction on the dimension. We have the paper on this, but general answer is it's question of the parameters and the question of the structure.
See no more questions. So let us thank all speakers.